There is a galaxy so distant and ancient that its light began its journey just 400 million years after the Big Bang, long before Earth, the Sun, or even our solar system existed. That galaxy is GN-z11. Its faint glow has traveled across 13.4 billion years of expanding space to reach us, carrying with it a message from the dawn of time. In studying it, we are not just looking at a faraway object, we are peering into the universe's forgotten youth, catching a glimpse of the moment when the first lights pierced the cosmic dark. But before we continue, subscribe to the channel so you don't miss out on any of these videos. If we could trace the history of the cosmos like flipping through the pages of a book, GN-z11 would be found just after the title page, one of the very first sentences in the grand story of everything. Existing a mere 400 million years after the Big Bang, GN-z11 is more than a distant smudge of light on a telescope image. It is a messenger from an era we've never seen with our own eyes, a time when the darkness of the early universe was only just beginning to lift. What makes GN-z11 so fascinating is that it shouldn't exist in the way that it does, not so soon, not so bright, not so active. The early universe was still settling, filled mostly with hydrogen gas, and hostile to the complex structures we see in galaxies today. Yet GN-z11 is out there, burning with unexpected brilliance, packed with star-forming energy, and flying in the face of what we thought the early cosmos should look like. When astronomers first spotted GN-z11, they realized they weren't just seeing far, they were seeing back. Back through time, through epochs when space was thick with fog, and light struggled to break free. Every photon from GN-z11 had to cross that abyss, dodging cosmic obstacles, and stretching with the expansion of the universe, just to end up on our detectors, faint, red, and ancient. This is why GN-z11 matters. It's a window into a time when galaxies were just beginning to awaken. And through it, we learn not just about stars or space, but about our origins, our beginnings, and what the universe looked like before anything like us could have even imagined it. To understand why GN-z11 matters so profoundly, we first need to recognize what it represents. This galaxy isn't just an object floating in the distant void, it's a time capsule. Its light, dim and redshifted by the expansion of space, has traveled across more than 13 billion years to reach us. That means when we look at GN-z11, we are witnessing the universe not as it is, but as it was mere moments after its birth. And in doing so, we get to observe a chapter of history that is otherwise hidden from view. In the vast timeline of the cosmos, 400 million years after the Big Bang is unimaginably early. The universe was still transitioning from a formless, opaque haze into a transparent, starlit expanse. It was the age when galaxies were first assembling themselves from the primordial gas left over from the Big Bang, when matter was clumping together under gravity's pull, igniting stars, and beginning to shape the large-scale structures that would one day become galaxy clusters, superclusters, and filaments. By discovering and studying galaxies like GN-z11, astronomers gain a window into that transformation. These ancient galaxies are the blueprints for everything that came after. They help us answer fundamental questions. How did the first galaxies form? How fast did they grow? What kind of stars did they produce? And how did those stars begin to influence the chemical makeup of the universe? Every time we find a galaxy from this early era, it challenges or supports the theoretical models we've built to describe cosmic evolution. GN-z11, in particular, shook the foundation of those models. According to our understanding, such a bright and well-formed galaxy shouldn't have existed so soon. It suggested that either star formation began earlier than we thought, or that some unknown processes accelerated the growth of early galaxies far beyond our expectations. This is why GN-z11 is more than a curiosity, it is a critical piece of the puzzle. It forces us to reconsider how galaxies evolve, how fast they can form stars, and how quickly structure emerged after the Big Bang. It narrows the gap between theory and observation, and in doing so, brings us closer to a coherent narrative of our universe's infancy. When we gaze at GN-z11, we are not just marveling at its age or distance. We are peering into the conditions that set the stage for everything to come. From the stars that forged the first elements heavier than hydrogen and helium, to the clouds of gas that coalesced into planets, to the long cosmic chain that eventually led to life. Understanding galaxies like GN-z11 helps us trace that lineage back to its beginning. And in that light, GN-z11 doesn't just matter, it is essential. GN-z11, despite the weighty role it plays in cosmic history, is remarkably humble in form. It's a tiny, faint galaxy, located an astounding 13.4 billion light-years away from Earth. When astronomers first detected it, what they actually saw was not a sweeping spiral or majestic elliptical shape, but a soft smudge of light, barely distinguishable from the blackness around it. Yet, that little smudge is one of the most significant discoveries in the story of our universe. To grasp what GN-z11 truly is, we must look at it through the lens of time and space. It is classified as a high redshift galaxy, which means its light has been stretched by the expansion of the universe as it journeyed to us. That stretching not only moves the light into the red part of the spectrum, it also tells us how long ago that light was emitted. In GN-z11's case, the redshift is so extreme that it places the galaxy's origin at just 400 million years after the Big Bang. This means GN-z11 formed at a time when the universe was still very young, chaotic, and mostly filled with hydrogen and helium gas. And yet, it had already managed to gather enough matter to create stars, generate light, and become visible across the cosmic void. What makes GN-z11 extraordinary is not just its distance but its character. It is a compact, high-energy galaxy, far smaller than galaxies we commonly observe, yet surprisingly bright. It's estimated to be only about a few thousand light-years across, a fraction of the size of galaxies like the Milky Way. Still, its star formation rate is astonishing, suggesting that it was producing new stars at a pace far faster than astronomers expected for such an early point in the universe's timeline. Despite being minuscule on a galactic scale, GN-z11 is intensely active. The stars within it are likely massive and short-lived, burning quickly and brightly, releasing powerful ultraviolet radiation. This light, redshifted through time, is what we detect now, barely visible, but rich with information. In essence, GN-z11 is a young, primitive galaxy in cosmic terms, a trailblazer of structure in a universe still emerging from darkness. It's a reminder that even in the earliest epochs, complexity and light were already taking shape in the vast silence of space. At 400 million years after the Big Bang, the universe was in the midst of one of its most dramatic and transformational epochs. This period is part of what astronomers call the Cosmic Dawn, a time when the first luminous objects began to form, and the once dark, opaque universe started to shine with starlight. To truly appreciate what GN-z11 represents, we have to place ourselves within the conditions of that primordial cosmos, when everything we take for granted today was only just beginning. Let's rewind. The Big Bang itself occurred approximately 13.8 billion years ago. In the aftermath of that colossal event, the universe was unimaginably hot, dense, and uniform. In the first few minutes, fundamental particles formed, and through nuclear fusion, light elements like hydrogen, helium, and trace amounts of lithium were created. But there were no stars, no galaxies, no structure. Just a sea of particles and radiation in a rapid expansion. It wasn't until about 380,000 years later that the universe cooled enough for atoms to form, primarily hydrogen. This event is known as recombination, and it allowed photons to travel freely through space for the first time. That ancient light is what we now detect as the cosmic microwave background, CMB. After recombination, the universe entered a long period of darkness, known fittingly as the Cosmic Dark Ages. With no stars yet ignited, there were no sources of visible light. Matter was starting to clump together under gravity's influence, but everything remained shrouded in darkness. Then came a new chapter, the era when gravity finally pulled enough matter into dense regions to form the first stars and galaxies. By the time we reach 400 million years after the Big Bang, these first stars had already begun to light up the cosmos. This is the moment in cosmic history when GN-z11 existed. It is a representative of this profound transition, from a cold, dark, neutral universe to one illuminated by the birth of stars and galaxies. At this time, the universe was roughly 3% of its current age. Its scale, though already vast, was much more compressed. Galaxies were tiny and chaotic, more like bright knots of gas and stars than the majestic spiral structures we're familiar with today. The cosmic web, the large-scale filamentary structure of matter in the universe, was in its earliest stages of development, still forming under the guidance of dark matter halos. Crucially, 400 million years after the Big Bang was also deep within the epoch of reionization. This was the process by which the intense ultraviolet light from the first generations of stars began to ionize the surrounding neutral hydrogen gas. Essentially, reionization is what turned the universe from a foggy, light-blocking environment into a transparent one, where photons could travel freely over cosmic distances. The universe became clearer, more open, allowing light from distant galaxies to eventually reach us billions of years later. However, during the time GN-z11 existed, this process wasn't complete. The intergalactic medium was still a murky mix of ionized and neutral hydrogen. That makes GN-z11's light even more impressive. It had to fight through this cosmic fog to get out into space, and eventually, to our telescopes. There were other things happening, too. The first black holes were forming, possibly seeded by the collapse of massive primordial stars. Early supernovae were already exploding, enriching their surroundings with the first heavy elements. These explosions played a key role in shaping early galaxy formation, stirring gas clouds, compressing material, and triggering waves of new star birth. This feedback loop of energy and matter recycling began laying the foundation for future stellar generations. But life, anywhere, was an impossibility at this stage. The elements essential for biology, like carbon, oxygen, and nitrogen, were only beginning to be produced in the hearts of those first stars. The heavier elements, the building blocks of planets, and eventually people, were still rare. The periodic table, in a cosmic sense, was only half written. The temperature of the universe then was far warmer than it is today. Not in the sense of stars burning, those were still scattered and new, but in terms of background temperature. The cosmic microwave background radiation, which is now just 2.7 Kelvin, would have been much warmer, around 50 Kelvin at that time. Though cold by human standards, that's over 10 times hotter than the present-day universe, and it highlights how everything, from temperatures to structure, was in a state of rapid evolution. Even the fundamental constants of physics, while thought to be unchanged, were being tested for stability in those conditions. This is why observing ancient galaxies like GN-z11 is not just a pursuit of distant light, it's a probe into whether the laws of physics themselves held steady across cosmic time. The early universe was also dominated by dark matter, an invisible form of matter that outweighs regular matter by more than 5-to-1. While we cannot see it, dark matter dictated the shape and pace of structure formation. Galaxies like GN-z11 likely formed within dark matter halos, gravitational wells that attracted gas and provided the scaffolding for galaxies to build upon. Without dark matter, GN-z11 might never have formed at all. In short, the universe 400 million years after the Big Bang was a place of firsts. The first stars, the first galaxies, the first elements heavier than helium. It was a universe still waking up, still violent and unstable, yet bursting with creative potential. GN-z11, shining in the darkness of that early age, stands as a beacon from this time, a relic of the earliest light-bearers in a universe just learning to shine. It reminds us that the cosmos wasn't always as calm and structured as it is now. What we see today, spiral galaxies, planetary systems, biological life, are all results of billions of years of evolution. GN-z11 is evidence that, even in the universe's youth, remarkable things were already beginning to unfold. To truly appreciate the significance of GN-z11, we need to understand just how far away it really is, and why that distance isn't as simple as measuring with a ruler. In astronomy, distance is tied to time, and when we speak of galaxies billions of light years away, we are not just describing their position in space, we're talking about their position in time. GN-z11 is a prime example of this complexity, and its astonishing remoteness is encoded in something known as redshift. Redshift is a key concept in cosmology. Imagine a galaxy emitting light in the early universe. As that light travels toward us, the universe itself is expanding, stretching the space through which the light moves. This causes the light's wavelength to stretch as well, shifting it toward the red end of the electromagnetic spectrum. The farther away the galaxy is, and the earlier in the universe it existed, the more pronounced this redshift becomes. It's like a cosmic Doppler effect. Just as a siren sounds lower in pitch as it moves away from you, light stretches into longer, redder wavelengths as its source recedes through expanding space. This redshift is measured with a variable called z, where a higher z means a greater redshift, and therefore a greater distance, and a deeper look back in time. GN-z11 has a redshift of z equals 11.09, which is mind-blowing in cosmological terms. It means that the universe has expanded more than 12-fold since the light from GN-z11 began its journey toward us. That number alone places GN-z11 among the most distant, and therefore the oldest, galaxies ever detected. But redshift doesn't just describe a galaxy's distance. It also tells us about the conditions of the universe when the light was emitted. A redshift of 11.09 corresponds to a time when the universe was only about 400 million years old, just a fraction of its current 13.8 billion year age. This is not merely an impressive measurement. It's a look into the infant universe, when the first galaxies were still forming and space was still transitioning from opaque to transparent. Now here's where it gets even more fascinating. GN-z11's redshift places it so far away that the light we see from it today began its journey before the Milky Way as we know it had even formed. That photon, just one tiny packet of light, left GN-z11 over 13.4 billion years ago. Since then, the universe has been expanding, stars have formed and died, planets have coalesced, and life has evolved on at least one tiny world. All while that ancient beam of light kept traveling, never stopping, never diverted, until it finally encountered the mirror of a telescope orbiting our planet. But because of the stretching of space itself, the actual distance to GN-z11 today is much greater than 13.4 billion light-years. That's just how long the light has been traveling. Taking into account the continued expansion of the universe, GN-z11 is now estimated to be about 32 billion light-years away in terms of comoving distance. In a very real sense, the galaxy is now vastly farther than the light travel time would suggest. And here lies one of the most profound ideas in astronomy. When we observe something like GN-z11, we're not seeing it as it is now, we're seeing it as it was. GN-z11, in its current state, if it even still exists, might look nothing like it did when it emitted the light we now detect. It may have merged with other galaxies, grown in size, evolved in complexity, or perhaps ceased to exist entirely. We will never see its present. What we see is its light from billions of years ago, a fossilized image from a time closer to the beginning of everything. Redshift, then, is not just a measurement of distance. It's a time machine. Each redshifted galaxy we discover is a portal to an earlier era, a flash of light illuminating a moment otherwise lost to history. GN-z11, with its redshift of 11.09, pushed the limits of what we thought was observable at the time it was discovered. It shattered previous records and opened the door to finding even older and more distant galaxies. It's important to note that determining redshift with such precision is no easy feat. It requires deep field imaging, long exposures taken with sensitive instruments like the Hubble Space Telescope. Astronomers analyze the spectrum of light from these distant galaxies, looking for specific signatures, such as the Lyman break or shifts in emission lines, that reveal how much the light has been stretched. For GN-z11, the redshift determination was made using this method, placing it confidently as one of the earliest and farthest galaxies ever observed. Even more exciting is that GN-z11's record wasn't just a momentary achievement. It stood as the most distant confirmed galaxy for years, acting as a reference point for models of galaxy formation and cosmic evolution. It helped astronomers refine their understanding of what kind of galaxies could exist so early in the universe and challenged assumptions about how fast and how efficiently galaxies could form. But GN-z11 didn't just expand our knowledge of cosmic distances, it redefined what was possible. Until it was found, few expected to detect such a luminous and compact galaxy at that extreme redshift. Its discovery revealed that the early universe may have been far more active and complex than we thought, with galaxies forming rapidly and emitting light strong enough to reach us across nearly the entire history of time. The sheer effort it takes to detect something with such a high redshift is staggering. It pushes our instruments to their limits. The Hubble Space Telescope, using its wide-field camera 3 with special filters optimized for infrared detection, captured GN-z11 at the very edge of its capabilities. In essence, GN-z11 sits on the outer rim of what our current generation of telescopes can perceive, a signal so faint, so redshifted, that only by carefully filtering out noise and stacking multiple exposures could it even be detected. And yet there it was. A single, distant, glowing knot of ancient starlight. A mark on an image that represents one of the earliest chapters of the cosmos. GN-z11's redshift is more than a number. It is a beacon in time, a cosmic signature that bridges the vast gulf between the universe's explosive birth and the present moment, when sentient beings can finally look up and wonder where it all began. GN-z11 first came into humanity's awareness thanks to one of the most remarkable instruments ever launched into space, the Hubble Space Telescope. In 2016, a team of astronomers using Hubble made a stunning announcement. They had found the most distant galaxy ever seen, a tiny speck of light whose photons had traveled more than 13.4 billion years to reach Earth. It was a discovery that pushed the limits of what we thought was even possible to detect and marked a historic milestone in the search for the universe's earliest galaxies. The Hubble Space Telescope, launched in 1990, had already revolutionized our view of the cosmos. Orbiting above Earth's atmosphere, Hubble avoids the blurring and light pollution that plagues ground-based telescopes, allowing it to capture crystal-clear images of deep space. But even more important for finding extremely distant galaxies like GN-z11, Hubble is equipped with sensitive infrared instruments, particularly the Wide-Field Camera 3, WFC3. This camera became the centerpiece in the hunt for galaxies from the early universe. Infrared detection is critical here because the light from such distant galaxies has been redshifted so heavily due to the expansion of the universe. What began as ultraviolet or visible light billions of years ago now reaches us as stretched-out infrared wavelengths. Hubble's WFC3 is capable of detecting this redshifted light, and it's precisely what enabled astronomers to find GN-z11. The discovery didn't happen by accident. It was the result of a systematic search through some of Hubble's deepest imaging campaigns, specifically the CANDEL's Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, and the GOOD's Great Observatory's Origins Deep Survey fields. These programs were designed to stare into seemingly empty regions of the sky for hundreds of hours, accumulating light from galaxies so faint and far away that they would be invisible in a single exposure. These deep fields act like cosmic core samples, drilling backward in time with every added hour of observation. Within these fields, the research team, led by Pascal Oesch and colleagues, identified a candidate galaxy that was unusually bright in the infrared filters and completely invisible in others. This was a classic signature of a high redshift object. They had found a galaxy that dropped out of visibility in shorter wavelengths due to what's known as the Lyman break, a point in the spectrum where ultraviolet light from young stars is absorbed by neutral hydrogen gas in the early universe. If a galaxy is far enough away, this break shifts into the infrared range. GN-z11's spectral energy distribution suggested a redshift of about 11.1, which would make it the most distant galaxy ever confirmed at that time. Still, a photometric redshift estimate, relying on the colors of the galaxy across different filters, wasn't enough. To confirm the finding, the team turned to spectroscopy, which breaks the light down into its component wavelengths and provides a far more precise measurement of redshift. They used the Mossfire spectrograph on the Kekai telescope in Hawaii, one of the most powerful ground-based observatories in the world. And even from the ground, GN-z11's signature held up. A distinctive emission line, a fingerprint of hydrogen, confirmed its astonishing distance. The announcement of GN-z11's discovery in 2016 sent ripples through the astronomical community. It didn't just push the record of the farthest known galaxy back by over 150 million years. It also suggested that galaxies could form, evolve, and shine brightly far earlier than expected. It hinted at a universe that was busier and more dynamic at a younger age than previously believed. But perhaps most inspiring was the way this discovery highlighted the power of human ingenuity. The Hubble Space Telescope had been in orbit for over 25 years by the time GN-z11 was discovered. Its instruments had been upgraded, its vision sharpened by servicing missions, and its scientific goals continually reimagined. Yet even so, no one could have predicted that Hubble would peer so deeply into the past that it would spot a galaxy born less than 500 million years after time itself began. It's worth pausing to imagine the actual process of discovery. Astronomers comb through thousands of faint galaxies in deep-field images, analyzing their light curves, their brightness profiles, their spectral shifts. It's like hunting for a single glowing ember in an infinite sea of darkness, an ember so distant and faint that only with meticulous analysis and cross-instrument verification can we confirm that it is real. GN-z11 was that ember. Its discovery also underscored the importance of international collaboration. Scientists from multiple countries, observatories, and institutions work together, combining space-based and ground-based data to push the boundaries of our observational reach. Without the precision optics of Hubble, the infrared capabilities of WFC3, and the follow-up spectroscopy from Keck, GN-z11 might have remained invisible, a flicker lost in the cosmic abyss. And it must be said, Hubble's role in this achievement was not just technical, but emotional. For a generation of scientists and space enthusiasts, Hubble had always been there, patiently watching the stars. That it could, so late in its life, deliver such a groundbreaking discovery is a testament to its design and the vision of the people who built it. GN-z11 was not just another data point, it was a triumph of persistence and curiosity. Its discovery by Hubble reignited questions about the nature of the early universe, about how quickly stars and galaxies could form, and about whether we might someday see even further, perhaps all the way to the very first galaxies. For a time, GN-z11 stood proudly as the farthest and earliest galaxy ever confirmed by science, a title earned not just by its staggering distance, but by the clarity and confidence of its redshift measurement. When it was announced in 2016 that GN-z11 possessed a redshift of 11.09, it shattered previous records and carved its place in the history of cosmology. It didn't just break the redshift record, it leaped over it. Before GN-z11, the highest confirmed redshifts hovered around z equals 8.6 to 10. These were already impressive, pulling our gaze to a time roughly 500 to 600 million years after the Big Bang. But GN-z11 went further, pushing the boundary of our observational reach to just 400 million years post-Big Bang, deeper into the cosmic past than anyone had thought possible with then current technology. This was not a small incremental step. It was a dramatic push into a darker, more mysterious corner of the universe. The importance of holding the redshift record cannot be overstated. Every galaxy found at a higher redshift becomes a milestone. Each one resets the limit of what's observable. And because higher redshift corresponds with earlier and more chaotic times in the universe's history, these discoveries directly challenge our understanding of how quickly matter organized into stars, galaxies, and larger structures. GN-z11's redshift of 11.09 meant that the universe was just about 3% of its current age when the galaxy's light began its journey toward us. It wasn't simply about the distance. It was about witnessing the universe in a phase that was previously invisible. Holding the redshift record meant GN-z11 became the cosmic benchmark, the reference point against which all future high redshift candidates would be compared. For years after its discovery, GN-z11 remained unbeaten. Despite rapid advancements in telescope technology and increasing depth in survey coverage, no other galaxy had been confirmed with a higher redshift through spectroscopic methods, a critical distinction. Many galaxies were proposed as candidates for being older or farther, but most were based on photometric redshifts, which, while useful, are less precise. Spectroscopic redshifts involve measuring specific emission or absorption lines in a galaxy's spectrum, providing a far more accurate reading. GN-z11's redshift of 11.09 was confirmed through spectroscopy using Keck Observatory's Mossfire instrument, making it robust and trustworthy. This reliability gave GN-z11 a kind of iconic status. It became the yardstick for the early universe, appearing in countless scientific papers, presentations, and models. If a galaxy was suspected to be older or more distant, it had to be compared to GN-z11. The question always followed: has it broken the GN-z11 record? And for years, the answer was no. During this time, GN-z11 helped shape our models of cosmic evolution. Its brightness, size, and star formation rate were all analyzed in the context of its extreme redshift, and its very existence pushed theorists to reconsider how fast galaxies could form and evolve. Its record status made it central to the study of reionization, the epoch during which early stars and galaxies ionized the intergalactic medium, making the universe transparent to ultraviolet light. Since GN-z11 was observed at the edge of this reionization window, it became a crucial piece of that cosmic puzzle. But as time went on, new instruments emerged, and with them came new contenders. The James Webb Space Telescope, JWST, launched in December 2021, was designed specifically to peer into the far infrared and break through the observational ceiling that GN-z11 had defined. Webb's vastly superior sensitivity and infrared range allowed it to detect galaxies that might lie even deeper in the past, further back than what Hubble could see. Indeed, in 2022 and 2023, a series of ultra-distant galaxy candidates emerged from JWST data. Some were estimated to be at redshifts greater than 12, even up to z equals 13 or more. One such candidate, known as CERS 93316, was initially believed to be at a redshift of around z equals 16.7, suggesting a light travel time from just 250 million years after the Big Bang. If confirmed, this would make it significantly older than GN-z11. However, as is often the case in early science, initial claims are subject to revision. Photometric estimates can be misleading due to contamination, misidentification of emission lines, or model assumptions. And so, despite exciting headlines, GN-z11's title stood firm until reliable spectroscopic confirmation of its challengers emerged. Even as newer galaxies potentially begin to surpass it, GN-z11's importance doesn't fade. Being the first galaxy confirmed beyond redshift 11 means it broke a barrier, scientifically and symbolically. It proved that it was not only possible to observe galaxies at such mind-bending distances, but also to analyze their properties with a high degree of confidence. It gave astronomers a solid foundation on which to push further. It also provided a scientific proof of concept that ultra-high redshift galaxies were not as rare or faint as once assumed. More than that, GN-z11 remained a teaching tool. Its discovery and confirmation methods were studied by astronomers and students alike. It served as a case study in how deep field surveys, photometric dropout techniques, and infrared spectroscopy could come together to reveal the oldest structures in the cosmos. And for the general public, GN-z11 became a kind of ambassador to the early universe. It made headlines. It appeared in documentaries and science journals. People who had never heard the term redshift before were suddenly learning about it because of GN-z11. It bridged the gap between the distant, abstract language of astrophysics and the innate human curiosity about where everything came from. So while its record may one day be surpassed, as all records eventually are, GN-z11 will always hold the distinction of being a first. It opened a new chapter in our quest to see the beginning. It marked the outer edge of Hubble's legacy. And it stood, for a moment in time, as the farthest known outpost of starlight in the observable universe. When we gaze at GN-z11, we're not merely observing something far away, we're reaching backward into the very history of the universe. It's difficult to grasp, but the light we detect from GN-z11 began its journey more than 13.4 billion years ago. That photon has been traveling through space longer than the Earth has existed, longer than the Sun has burned, and even longer than galaxies like the Milky Way had fully formed. In the most literal sense, observing GN-z11 is peering through time. And this is one of the most mind-expanding truths of cosmology. In everyday life, we perceive the world as it is now. When we look at a mountain, a building, or another person, we see them in what feels like real time. But even this is an illusion of sorts. Light takes time to travel, and even on Earth, there's always a delay, minuscule though it may be. The moon we see is 1.3 seconds old. The sun is 8 minutes and 20 seconds in the past. But as the distances increase, so does the delay, and on cosmic scales, this delay stretches into epochs. With GN-z11, the delay is measured not in minutes, hours, or years, but in eons. We're seeing it not as it is now, but as it was when the universe was still in its infancy. Imagine this: GN-z11's light left the galaxy 13.4 billion years ago, and in that time, our universe has expanded vastly. Civilizations have risen and fallen, stars have been born and died, entire galaxies have collided, and all the while, that faint stream of photons from GN-z11 has been moving steadily through space, crossing unimaginable gulfs of darkness. It has passed ancient quasars, skirted vast voids, and perhaps even brushed the edges of long-dead galaxies. And only now, in our present moment, does it arrive, softly hitting the mirrors of our telescopes and registering as the faintest glow in the void. This is the power of astronomy. We don't just see far, we see back. Telescopes like Hubble are not just tools for observation, they are time machines. They allow us to reconstruct history not from fossils or ruins, but from light itself. Every photon carries with it the story of its origin, the conditions of its source, the energy of its emission, and the path it traveled. When that light finally reaches us, it tells us what the universe was like at a moment long gone. GN-z11 is a relic from an age before Earth existed. Our planet formed about 4.5 billion years ago, 9 billion years after the light from GN-z11 began its journey. The sun hadn't ignited. The Milky Way's spiral arms weren't shaped. Life, as we know it, was an unfathomable possibility. And yet, this ancient galaxy was already blazing with the formation of stars, creating its own structure in a cosmos that was only 400 million years old. This realization is both humbling and awe-inspiring. It means that the universe was already full of creative processes, star formation, galaxy building, elemental synthesis, long before our solar system even began to swirl out of dust and gas. By looking at GN-z11, we aren't just studying a galaxy. We are witnessing the very processes that made galaxies possible. It's also worth appreciating the fragility of this cosmic message. Light is easily disrupted. It can be absorbed, scattered, or blocked by interstellar dust, gas clouds, and other celestial objects. The fact that GN-z11's light managed to survive its voyage, undisturbed enough to be detected and analyzed, is nothing short of miraculous. It arrived as a whisper, almost lost to time, but carrying within it the signature of its birth. The wavelengths stretched, the photons redshifted, the spectrum marked by hydrogen lines that signal its origin. Through GN-z11, we are granted a rare and precious connection to a past we could never otherwise touch. No spacecraft could ever travel there. Even if we could somehow jump to the present-day location of GN-z11, now over 32 billion light-years away due to the universe's continued expansion, we wouldn't see it as it was. We'd see its modern form, whatever that may be, evolved, merged, or perhaps even extinguished. The galaxy that emitted the light we detect may no longer exist in any recognizable way. But its past still does. Because its past light is still arriving. This is the poetry of cosmic observation. The farther we look, the older the universe appears. In deep-field images from telescopes, every speck of light is a time-stamped message from the past. Some are a few million years old. Others are billions. And among the oldest, sitting on the very edge of our vision, is GN-z11. It's a snapshot of a time we cannot otherwise experience. A snapshot of the era when darkness was just beginning to lift. When stars were rare and precious. When galaxies were no more than chaotic swirls of gas, glowing dimly against a backdrop of cold hydrogen. GN-z11's light shows us that the early universe wasn't empty. It was already alive, with activity, with structure, with light. This is more than a scientific achievement, it's a philosophical one. It shows us the interconnectedness of time, space, and existence. It proves that the universe has a memory. That memory is light, and when we build the right tools, telescopes, detectors, instruments, we can read it. So when we speak of peering through time, we're not speaking metaphorically. We are literally looking back, catching photons that began their journey before any human eye had ever opened. GN-z11 is a lens into that era. It tells us, with soft urgency, that the universe was not always the way it is now, and that it took billions of years of cosmic evolution to sculpt the stars, galaxies, planets, and people that now look back. Detecting a galaxy as ancient and distant as GN-z11 is a monumental achievement, but confirming its existence and verifying its distance is an even greater challenge. In the vastness of the cosmos, where distances are measured in billions of light-years and signals are little more than whispers in the void, separating truth from illusion becomes a delicate and precise science. The struggle to confirm GN-z11 was no exception. It involved complex techniques, multiple instruments, and a careful unraveling of cosmic clues. And even then, the results had to stand up to global scientific scrutiny. One of the first and most daunting challenges astronomers face is the extreme faintness of the signal. GN-z11 is not a galaxy you can simply see in a traditional sense. It doesn't appear as a bright object in the sky. It shows up as a barely perceptible smudge, a pale point of light on a deep field image captured over hundreds of hours. At such enormous distances, galaxies appear tiny and dim, requiring painstakingly long exposure times to gather enough photons to even register their presence. And once that light is captured, the question becomes, is this object what we think it is? At such high redshifts, the signal is buried deep in the infrared portion of the spectrum. The universe's expansion has stretched the original ultraviolet and visible light of the galaxy into longer and longer wavelengths. This redshift is both a tool and a problem. It helps us identify how far back in time we are looking, but it also means we need instruments that are incredibly sensitive to infrared light. Even with the advanced capabilities of the Hubble Space Telescope and its Wide-Field Camera 3, there's a limit to how much light can be captured. And what's worse, infrared light is easily contaminated by Earth's atmosphere, by instrumental noise, or even by other cosmic objects emitting similar wavelengths. This leads to the second major challenge, distinguishing genuine high redshift galaxies from imposters. There are many things in the universe that can mimic the colors and characteristics of a distant galaxy. For example, dusty, red galaxies that are much closer to us can appear similarly dim and infrared bright. These low redshift interlopers can easily be mistaken for ancient galaxies unless we have precise enough data to rule them out. That's why astronomers rely heavily on something called spectroscopy, the gold standard for measuring redshift. Spectroscopy involves dispersing the light from a galaxy into its component wavelengths, like a prism spreading white light into a rainbow. In this spectrum, scientists look for telltale features, especially emission lines like the Lyman alpha or hydrogen beta lines. These act as cosmic barcodes. Their positions along the spectrum tell astronomers exactly how much the light has been stretched, and therefore, how far it has traveled. But here's the catch: obtaining a clean, readable spectrum of such a faint and distant object is incredibly difficult. Spectroscopic instruments need a lot of light to work with, and GN-z11 just doesn't produce much of it. When astronomers attempted to collect its spectrum using the Keck telescope's Mossfire spectrograph, they had to fight not just low signal strength but also sky noise, cosmic ray interference, and instrumental limitations. It was like trying to hear a whisper in the middle of a hurricane. The team succeeded, barely. They detected a faint emission line believed to be the Lyman alpha line at a redshift of 11.09. But even that detection was met with healthy skepticism from the scientific community. Was the line real? Was it really Lyman alpha? Or could it be something else, a misidentified line from a lower redshift object? These questions aren't just academic. They determine whether the object genuinely pushes the frontier of cosmic history or not. Moreover, confirming redshift is not enough. Astronomers must also confirm that the light belongs to a galaxy and not something more exotic, like a quasar, a starburst region, or even a fluke in the data. They analyze the object's morphology, its shape and structure, and compare it with models of what early galaxies should look like. GN-z11 appeared compact and bright, with a concentrated region of star formation, which fit expectations, but confirmation still required multiple lines of evidence. The limitations of current telescopes also add to the struggle. Hubble, for all its brilliance, was never optimized for extreme infrared detection. Even with WFC3, it couldn't reach the farthest edges of redshift where light becomes nearly impossible to detect. Ground-based observatories like Keck face their own hurdles. Earth's atmosphere absorbs much of the infrared light, limiting observational windows and requiring corrections for atmospheric interference. It's like trying to see through a fogged-up window into a distant candlelit room. To complicate matters further, astronomers must deal with instrumental artifacts, false positives, and statistical noise. A single misinterpreted signal could throw the entire redshift estimate into question. That's why the confirmation of GN-z11 wasn't declared immediately. It followed a rigorous process of cross-checking photometric and spectroscopic data, comparing it with simulations, and submitting the findings to peer-reviewed journals for validation by other experts in the field. And even then, the confirmation of GN-z11 as the farthest galaxy was made with a sense of cautious excitement. Astronomers were thrilled, but they also understood the fragility of such claims. In science, especially at the edge of observation, every result is provisional. New data, more advanced instruments, or subtle corrections could always revise the picture. The announcement in 2016 was more than just a scientific finding. It was the culmination of years of observation, analysis, debate, and verification. It was a triumph not just over distance, but over doubt. It required collaboration between space-based telescopes, ground observatories, and theoretical astrophysicists. And perhaps most importantly, it revealed how difficult it is to truly know what's out there in the early universe. Every distant galaxy we confirm is a conquest of both technology and understanding. It's not enough to take a picture, we must decode the faint messages from the dawn of time, separate truth from illusion, and build a narrative supported by data that is both fragile and profound. GN-z11 taught us that with persistence, precision, and a little bit of cosmic luck, it is possible to look further back than we ever dreamed, and to confirm what, at first glance, seems almost impossible. Though GN-z11 stands tall in cosmic history as one of the earliest known galaxies, in physical size, it's a miniature when compared to modern galactic giants like our Milky Way. In fact, GN-z11 is estimated to be only about 1% the size of the Milky Way, a detail that underscores not only how galaxies evolve over time, but also how remarkably compact the early universe was when structures like this were just beginning to form. To visualize this contrast, let's first consider the Milky Way, a vast spiral galaxy stretching roughly 100,000 light-years in diameter. It contains hundreds of billions of stars, sprawling arms of gas and dust, a dense central bulge, and a massive halo of dark matter. It's a mature and stable galactic ecosystem, shaped by billions of years of gravitational interactions, star births and deaths, and mergers with other galaxies. Now shrink that down. GN-z11, by contrast, measures approximately 2,500 to 3,000 light-years across. That's smaller than many of the Milky Way's spiral arms alone. To place this in perspective, if the Milky Way were a full-sized, mature tree with a wide-reaching canopy, GN-z11 would be a seedling, alive, growing, full of potential, but tiny in comparison. But don't let that size fool you. Despite its diminutive scale, GN-z11 was furiously active, especially in terms of star formation. While the Milky Way creates about 1 or 2 new stars per year in its current mature state, GN-z11, even at its early stage, was forming stars at a rate of around 20 solar masses per year. That's 10 to 20 times faster than our galaxy today, an extraordinary pace for something so small and young. This size difference is key to understanding galactic evolution. Galaxies in the early universe were denser, more irregular, and less structured. GN-z11 likely didn't yet have the elegant spiral arms or rotational symmetry we associate with large galaxies. Instead, it was a clump of hot, glowing gas undergoing intense bursts of star formation. Gravity had only just begun to pull matter together into the kind of coherent systems that would eventually become the majestic galaxies we see in the modern universe. Its compactness also meant GN-z11 was extremely efficient. The gas and dust available for star formation were tightly packed, leading to a high star formation efficiency. This was likely a product of its environment, formed in a time when the cosmic web of gas was denser and more richly laced with the raw ingredients for building stars. Moreover, because light from GN-z11 is redshifted and faint, it's difficult to resolve its internal structure in detail. The best we can observe is that it appears bright, compact, and slightly elongated, which suggests either an irregular shape or possibly a merger event already underway, even at that early stage. It's not uncommon for early galaxies to grow through mergers, where multiple clumps of matter come together under the pull of gravity to build larger structures. The Milky Way, too, likely started this way, growing by consuming smaller galaxies over billions of years. What's most fascinating is that GN-z11 represents a kind of primordial blueprint. It's a cosmic embryo, showing us the basic ingredients and processes that will, over eons, produce much larger, more ordered systems. In a universe still in its cosmic dawn, a galaxy like GN-z11 might have been common, small, blazing hot, producing stars at breakneck speed, and destined to either grow through accretion or be absorbed into larger galaxies as the cosmic structures matured. And consider this, the size discrepancy also speaks to how much space itself has changed. The Milky Way didn't just grow in mass and diameter over time, it grew in an expanding universe. The very fabric of space stretched between galaxies. What was once close-knit and compact became more diffuse. GN-z11 was born into a universe that was far smaller and denser overall. Every inch of space was more tightly packed with material, and distances between galaxies were far less than they are now. Yet, despite all of that, GN-z11's light reached us. From that tiny, bright smudge, so compact it would barely fill a pixel in many telescope images, came the oldest starlight ever confirmed by spectroscopy. A 3,000 light-year-wide cluster of youthful stars, gas, and dust, blazing against the backdrop of an emerging cosmos, its size dwarfed by today's galactic standards, but its importance towering in our understanding of where we came from. It's this very contrast between GN-z11's physical smallness and its historical greatness that makes it so profound. It reminds us that in the early universe, big things often came in small packages. That size does not determine significance. And that sometimes, the tiniest galaxies can whisper the loudest truths across the oceans of time. Despite its extreme distance, so far that its light began its journey when the universe was less than 3% of its current age, GN-z11 is surprisingly bright. This unexpected luminosity caught astronomers off guard when it was first discovered. At such an early cosmic epoch, galaxies were expected to be small, dim, and still forming the first generation of stars. And yet, GN-z11 shone through the veil of cosmic time with a clarity that not only allowed it to be detected by Hubble but also made it stand out among the faint, primordial objects littering the deep field images. Why? To understand GN-z11's surprising brightness, we need to look at several interwoven factors: its star formation rate, stellar population, compact structure, lack of dust, and the fundamental physics of early galaxy growth. First and foremost, GN-z11 is undergoing an intense burst of star formation. Observations suggest that it is forming stars at a rate of about 20 solar masses per year, which, for a galaxy of its size and age, is incredibly fast. For comparison, the Milky Way, which is vastly larger and more evolved, forms only about 1 to 2 solar masses of stars annually. GN-z11's star formation rate is roughly 10 to 20 times more efficient per unit mass. This rapid generation of hot, massive stars, particularly the short-lived, high-mass, blue O and B-type stars, produces copious amounts of ultraviolet light, which is then redshifted into the infrared range by the time it reaches us. What makes this even more impressive is that such massive stars don't live long. Their lifespans are measured in just a few million years. So, for GN-z11 to appear this bright, its starburst activity had to be ongoing right at the moment its light was emitted. It wasn't a flicker, it was a sustained blaze. The galaxy was caught in a moment of intense stellar creation, flooding its region of space with radiation and making it easier to detect despite its vast distance. Next, we consider its stellar population. Early galaxies like GN-z11 likely contain mostly population 3 and early population 2 stars, stars formed from nearly pristine hydrogen and helium, with very few heavier elements, metals. These low metallicity stars tend to be more massive, hotter, and more luminous than the stars forming today. Without metals to cool the gas and moderate collapse, the first stars burn brighter and faster, contributing to the unexpectedly high luminosity. GN-z11's compact structure also played a role. Because it is so small, about 2,500 to 3,000 light-years across, all of its star-forming material is densely packed into a relatively tiny volume. This high density means that energy emitted from young, hot stars doesn't dissipate across vast distances. Instead, the energy is concentrated, leading to higher surface brightness. It's the difference between a tightly clustered flame and a loosely scattered spark. Even a small galaxy, if densely packed and efficient at producing stars, can appear luminous. Additionally, GN-z11 appears to have relatively low dust content, which is crucial. Dust absorbs and scatters ultraviolet and visible light, re-emitting it in far infrared wavelengths. In mature galaxies, especially those forming stars at high rates, dust can obscure much of the energetic radiation. But in GN-z11, the universe was still young. There hadn't been enough generations of stars to produce heavy elements in significant quantities, and thus less time to form dust. The result? More of the galaxy's ultraviolet light escaped directly into space, unimpeded, and eventually reached us. There's also the possibility of gravitational lensing, where light from a distant object is magnified by a massive object, like a galaxy or galaxy cluster, that lies between it and the observer. However, in GN-z11's case, astronomers found no strong evidence of lensing magnification. Its brightness seems to be intrinsic, not boosted by external factors, which makes the result even more remarkable. It truly is bright for what it is and where it is. Another subtle yet important factor is that GN-z11 is likely undergoing a cosmic growth spurt. Early in the universe's life, galaxies didn't grow smoothly and slowly. Instead, they formed rapidly in fits and starts, triggered by collapsing gas clouds, mergers with other proto-galaxies, and tidal interactions. This kind of rapid formation generates chaotic but highly productive environments, places where the gravitational collapse of gas triggers entire waves of starbirth. GN-z11 may have been caught in one of these rare, powerful bursts, a snapshot of a galaxy in the middle of building itself. And finally, consider the context of the cosmic background. The universe was much darker then, literally. The cosmic microwave background had long cooled, but large-scale reionization was still incomplete. The space between galaxies was filled with neutral hydrogen that absorbed most high-energy photons. So when a galaxy like GN-z11 was able to break through that fog and shine, it did so against a darker backdrop, making it stand out even more starkly in deep-field observations. In short, GN-z11's brightness is the result of a rare confluence of conditions. It's a small but furiously active galaxy, filled with hot young stars, lacking in obscuring dust, and compact enough to concentrate its light into a powerful beam across the universe. Its luminosity is both an artifact of its environment and a clue to its nature, a beacon from a time when the universe was only beginning to organize itself into the cosmic structures we know today. That brightness wasn't expected. It challenged astronomers' models of how quickly galaxies could form and shine. It suggested that even in the first few 100 million years, conditions allowed for the formation of luminous, active galaxies. And it reminded us that the universe, even in its earliest chapters, was not quiet. It was ablaze with creation. One of the most astonishing features of GN-z11 is not just that it exists so soon after the Big Bang, but that it is already forming stars at a rate that rivals or exceeds much more mature galaxies. Observations estimate that GN-z11 is producing around 20 solar masses worth of stars per year, a number that forces us to rethink what early galaxies were capable of. To understand how extreme this is, we need to consider what such a star formation rate, SFR, implies for a galaxy that is only 400 million years into cosmic history. To put it in perspective, the Milky Way, a massive and evolved spiral galaxy roughly 13.6 billion years into its existence, forms about 1 to 2 solar masses per year. That includes giant molecular clouds, spiral density waves, and all the processes refined over eons to fuel star birth. Yet here is GN-z11, barely 1,000th the mass and only 3% into the universe's age, already churning out stars at 10 to 20 times the rate of our galaxy today. That's not just impressive. It's unprecedented. This finding immediately poses a problem for existing models of galaxy formation. According to standard cosmological theories, galaxies in the early universe should have taken time to accrete matter, condense gas, and build up the conditions necessary for large-scale star formation. It was assumed that the early universe was too chaotic and unstructured for sustained starburst activity. Yet GN-z11 is not only surviving in that environment, it's thriving. So, what drives this astonishing pace of stellar birth? The answer begins with abundant cold gas, the raw fuel for star formation. In the early universe, intergalactic space was dense with hydrogen and helium, the simplest and most common elements, produced in the first few minutes after the Big Bang. Galaxies like GN-z11 were likely swimming in these vast cosmic reservoirs, continuously drawing in fresh gas from their surroundings. Because this gas had not yet been enriched with metals, elements heavier than helium, it behaved differently. Low metallicity gas cools more slowly, but under the right conditions, it can collapse into stars very efficiently, especially when it is dense and turbulent. And GN-z11 was small, just a few thousand light-years wide. That meant the inflowing gas didn't have to travel far to reach the regions where stars were forming. The compactness of the galaxy allowed it to rapidly concentrate material, creating dense clouds that could collapse under gravity. These clouds formed stars in clustered, intense bursts, without the need for the more regulated processes seen in large, stable galaxies today. Another factor is that in GN-z11's epoch, feedback mechanisms, the processes by which star formation is regulated, were likely less developed. In modern galaxies, supernova explosions, stellar winds, and black hole activity create turbulence and heat that blow gas out of star-forming regions or prevent gas from collapsing. This self-regulation slows star formation over time. But GN-z11 might not yet have had the supermassive black holes or evolved stellar populations to create this feedback. As a result, the galaxy could have entered a kind of runaway phase, an unchecked growth spurt where star formation spiraled upward without resistance. Interestingly, the stars forming in GN-z11 may also be very different from those born today. In an environment so early, with virtually no heavy elements, the initial mass function, IMF, a description of how many stars form at different sizes, might have been skewed toward more massive stars. These massive stars burn brighter and die faster, contributing significantly to the galaxy's brightness and chemical evolution. If GN-z11 was producing a higher proportion of these short-lived giants, its luminosity would spike, and its feedback loops would kick in sooner, possibly ending the burst quickly. But until that happened, it would shine with intense brilliance. The implications of this are huge. GN-z11 shows us that galaxies didn't need billions of years to become active. They could go from chaotic gas clouds to fully operational star factories in a few 100 million years. That's lightning fast on cosmic timescales. And it challenges models that assumed galaxies required prolonged gestation periods before forming stars in significant numbers. Moreover, this high star formation rate also ties into cosmic reionization. GN-z11 existed during a period when the universe was transitioning from opaque to transparent. The ultraviolet radiation from galaxies like GN-z11 contributed to the reionization of neutral hydrogen gas, allowing light to travel freely across space. A galaxy forming stars this fast would have emitted large amounts of UV radiation, making it a prime candidate for helping to turn the lights back on in the early universe. What makes this even more remarkable is the galaxy's youth. GN-z11's estimated age is just 40 to 70 million years at the time we observe it. That means it may have started forming stars as early as 330 million years after the Big Bang, or perhaps even earlier. Its starburst phase wasn't a fluke, it was part of its very origin. In fact, GN-z11 may represent one of the first wave of galaxies to ignite significant star formation. Its structure and energy output are telling us that galaxies were not just assembling early, they were already evolving, already influencing their environment, and already acting as engines of cosmic change. It also raises deeper questions. If GN-z11 could form stars this quickly, how many other galaxies like it were missed because they had shorter, dimmer, or more dust-obscured bursts of activity? Was GN-z11 an outlier, or a common type of object that we're only now learning to detect? The James Webb Space Telescope will help answer that, but GN-z11 remains the first to show us just how fast the cosmic engine could rev up. In essence, GN-z11 is a cosmic sprint runner at the beginning of a marathon. While we expected a slow jog from the early universe, GN-z11 was already at full stride, building stars at breakneck speed. It is not just old, it's ambitious. Not just small, it's explosive. And by forming stars so rapidly, it opened our eyes to the raw, untamed energy of the young universe. The chemical composition of GN-z11 offers a rare glimpse into the elemental beginnings of the cosmos. Unlike the complex and metal-rich galaxies we see in the modern universe, GN-z11 was formed during a time when the periodic table was still in its infancy, cosmically speaking. In astronomy, when we talk about metals, we don't mean just iron or copper, we mean all elements heavier than hydrogen and helium. These elements are forged in the hearts of stars and released into space through supernovae. So the presence, or absence, of metals in a galaxy like GN-z11 tells us everything about its history, age, and the cosmic processes unfolding within it. One of the most striking aspects of GN-z11 is its low metallicity. This aligns with expectations, given its position in time, just 400 million years after the Big Bang. At that point, the universe had only recently transitioned from the Dark Ages, and stars had only begun to forge the elements that would eventually form planets, life, and everything we know. The first generation of stars, known as Population 3 stars, were made almost entirely of hydrogen and helium. They were massive, short-lived, and burned incredibly hot. When they exploded in supernovae, they seeded the interstellar medium with the first heavy elements. If GN-z11 formed shortly after this first wave of star death, then its gas clouds would have been lightly sprinkled with metals, just enough to ignite star formation more efficiently than before, but still significantly more primitive than anything we see today. Spectroscopic studies of GN-z11's light, as faint and difficult as they are, suggest that the galaxy had already undergone some chemical enrichment, meaning it was not the very first generation of stars, but among the first few waves. This low but non-zero metallicity is a fingerprint of rapid evolution. What makes this particularly revealing is that GN-z11 seems to be chemically evolving faster than expected. Its relatively high star formation rate is generating more heavy elements at a pace that rivals larger galaxies from later epochs. Every new supernova explosion from a massive star within GN-z11 adds a bit more carbon, oxygen, silicon, and iron to the interstellar gas. These metals then get incorporated into the next generation of stars, gradually increasing the galaxy's overall metallicity in what's known as chemical feedback. That GN-z11 already shows signs of this loop means that its life cycle, from gas cloud to star, to supernova, and back to enriched gas, was happening very rapidly. This tells us two things. First, GN-z11 likely began forming stars very early, possibly within a few 100 million years after the Big Bang. That's incredibly fast, given that the universe was still settling down from its violent birth. Second, it implies a certain efficiency in recycling stellar material, a trait that was thought to develop later, in more mature galaxies. In GN-z11's case, it was already underway, revealing a galaxy that, though small, was chemically dynamic and evolving at breakneck speed. Another clue comes from the absence of certain elements. The lower levels of nitrogen, for instance, suggest that GN-z11 hadn't yet formed many low-mass stars, which live longer and take time to produce nitrogen through their stellar processes. Similarly, the lack of significant dust, largely formed from metals, also indicates that heavy elements were still scarce. This fits with the general model of a primordial environment still dominated by light gases but beginning to transform. Yet this scarcity doesn't equate to weakness. Quite the opposite. Low metallicity environments are often more conducive to the formation of very massive stars. Without metals to cool the gas efficiently, collapsing clouds tend to fragment less and form larger stars. This might partially explain GN-z11's high brightness and rapid evolution. Its environment favored the birth of hot, luminous, short-lived stars that could quickly enrich the galaxy, trigger further star formation, and dramatically alter its chemical makeup in a relatively short amount of time. From a broader perspective, GN-z11's metallicity offers key insights into the timeline of cosmic metal production. It acts as a timestamp in the universe's chemical evolution, helping astronomers chart how quickly stars were forming and dying in the early universe. Its composition supports the idea that by 400 million years after the Big Bang, the universe had already begun producing complex elements, not in abundance, but in detectable, meaningful quantities. What's perhaps most fascinating is that even with such limited metal content, GN-z11 managed to become one of the brightest, most active galaxies in its era. It didn't need the complex chemistry of mature galaxies. It was a raw, untamed furnace, generating light and heavy elements as it went. Its chemical simplicity, far from being a limitation, may have actually been the key to its explosively rapid evolution. This metallic fingerprint also distinguishes GN-z11 from foreground contaminants, galaxies that might masquerade as ancient, high redshift objects due to their color or brightness but are actually closer and richer in metals. GN-z11's spectral lines, shaped by its chemical contents, match the profile expected of a truly ancient galaxy, reinforcing its authenticity and providing a layer of confirmation separate from redshift alone. As technology improves and we study more galaxies like GN-z11, especially with instruments like the James Webb Space Telescope, we will gain even sharper readings of these elemental signatures. Each metal line tells a story of stars that once lived, exploded, and changed the makeup of the universe. In GN-z11, those stories are just beginning, written in a simpler alphabet of hydrogen, helium, and the first whispers of carbon and oxygen. It's like reading the first pages of a cosmic novel, written in fire and starlight. The light we receive from GN-z11 is not just a faint glow from a distant galaxy, it's a time capsule, a detailed record of physical conditions that existed over 13.4 billion years ago. And though the galaxy is far beyond the reach of any spacecraft, the photons it sent out have been traveling all this time, carrying within them the fingerprints of their origin. These photons don't simply tell us that GN-z11 exists, they tell us what it is, how it formed, and what the universe was like when it began to shine. But how do we extract that kind of deep insight from something as fragile as light? We do it through the powerful method of spectroscopy, the science of breaking light down into its constituent wavelengths. Just as a prism separates white light into a rainbow of colors, a spectrograph takes the faint light from GN-z11 and spreads it out into a spectrum, a stretched-out band that reveals how much energy is emitted at each wavelength. And within that spectrum lie a series of critical signatures that serve as clues to the galaxy's identity and nature. One of the first things astronomers look for is emission lines, bright peaks in the spectrum that are produced when atoms in the galaxy are excited and emit light at very specific energies. Each element emits light at unique wavelengths, so when we observe an emission line, we know exactly which atom created it. Hydrogen, the most abundant element in the universe, produces a series of spectral lines that are especially important, including the Lyman alpha line, which occurs at a wavelength of about 121.6 nanometers in the ultraviolet range. However, due to the cosmic redshift, the light from GN-z11 has been stretched as space itself expanded over the last 13.4 billion years. That Lyman alpha line, originally in the ultraviolet, has now been shifted far into the infrared part of the spectrum, landing around 1.47 microns in GN-z11's case. This shift is what gave GN-z11 its redshift measurement of z equals 11.09, placing it among the most distant galaxies ever confirmed by spectroscopy. Measuring that redshift is the first step to determining the galaxy's distance, age, and its position in cosmic history. But beyond distance, the spectrum tells us about temperature, chemical composition, star formation rate, and motion. The relative strengths of different emission and absorption lines can indicate what kinds of stars dominate the galaxy: young, massive, hot stars, or older, cooler ones. In GN-z11's case, the spectrum revealed strong ultraviolet emission, suggesting a large population of young, massive stars. These are stars that burn brightly and die young, evidence of intense, ongoing star formation. The absence or weakness of metal lines in the spectrum also confirms GN-z11's low metallicity, supporting the conclusion that it was formed before heavy elements had significantly accumulated in the universe. Spectral signatures of elements like oxygen, nitrogen, and carbon are faint or missing altogether, a pattern consistent with a galaxy still chemically primitive, just beginning its journey through stellar cycles and enrichment. Another remarkable insight comes from the shape of the continuum, the overall slope of the galaxy's light across all wavelengths. If the spectrum drops steeply at shorter wavelengths, which are now seen in the infrared due to redshift, it may indicate the presence of dust, which absorbs and scatters blue and ultraviolet light. But GN-z11's spectrum shows a relatively clear continuum, reinforcing the idea that dust is minimal, allowing most of the starlight to escape without obstruction. This clarity helps explain why GN-z11 is visible at all, despite its distance. Spectroscopy also allows us to estimate the star formation rate. Certain lines, particularly those emitted by ionized hydrogen regions, H2 regions, scale with the number of young, massive stars present. By measuring the strength of these lines, astronomers deduce how many stars are being born. GN-z11's spectral features suggest a very high star formation rate, consistent with its brightness and compactness. But the process is not easy. To study GN-z11's spectrum, astronomers had to rely on some of the most advanced instruments available at the time, including the Mossfire spectrograph on the Keck telescope in Hawaii. They focused on the infrared range, where the redshifted emission lines of GN-z11 would appear. The observations required extremely long exposures, carefully timed and calibrated to minimize noise and atmospheric interference. Even then, the signals were faint, barely distinguishable from the background. Yet, with enough persistence and data processing, the Lyman alpha line emerged, confirming the galaxy's extraordinary distance and youth. Now, with the James Webb Space Telescope, spectroscopy has taken an enormous leap forward. Its infrared instruments, like NIRSpec, are specifically designed to capture the kinds of spectra emitted by early galaxies like GN-z11. Future observations may reveal fainter lines, subtler chemical features, and even kinematic data, information about how gas and stars are moving within the galaxy. All of this comes from light alone, encoded in wavelengths, absorbed by mirrors, and interpreted by computers and human minds. In essence, light is the only messenger we have from GN-z11. It's all we can rely on to learn about a galaxy so far away that its light began its journey when there were no planets, no people, no galaxies like the Milky Way. Through spectroscopy, that light becomes a story. It tells us how fast the galaxy was forming stars, what kinds of atoms were present, how much dust obscured its starlight, and whether it was already influencing its surroundings. The most remarkable part? This light isn't new. It's ancient. Every photon arriving from GN-z11 left that galaxy when the universe was still cloaked in hydrogen fog. That it reached us at all is extraordinary. That we can decode it into elements, temperatures, movements, ages, is a testament to human ingenuity and our relentless desire to understand the cosmos. Studying the spectrum of GN-z11 is like listening to the faint echo of a song sung at the dawn of time. Each note, each wavelength, tells us something about the voice that sang it and the world it came from. In that way, spectroscopy becomes not just a tool of science, but a form of cosmic archaeology. It lets us read light as if it were language, revealing, line by line, the earliest chapters of our universal story. When we speak of the universe in its infancy, we often imagine it as a scattered sea of gas and darkness, a formless soup waiting to become galaxies and stars. But even in those earliest times, the universe was not truly random. Beneath the surface chaos of collapsing hydrogen clouds and exploding young stars, a grand structure was already taking shape. This is what cosmologists call the cosmic web, a vast network of filaments, nodes, and voids, woven from the primordial fluctuations seeded during the Big Bang. GN-z11 didn't just exist in isolation. It lived within the early scaffolding of this web, one of the first lights flickering into existence in the densest threads of cosmic matter. The cosmic web is built on dark matter, an invisible form of mass that doesn't emit or absorb light, but dominates the gravitational structure of the universe. In the first few 100 million years after the Big Bang, dark matter began to clump together under gravity. These clumps formed halos, regions of increased density, that would eventually attract ordinary matter, baryons, to their centers. The densest intersections of these dark matter filaments became nodes where galaxies could form, while the spaces in between grew into voids, vast, empty regions that would expand as the universe aged. GN-z11 likely formed at the intersection of multiple filaments in one of these early nodes. Its presence is a strong indicator that this galactic framework was already well underway just 400 million years after the universe began. While the cosmic web would eventually grow to span billions of light years with large clusters and superclusters of galaxies, in GN-z11's time, it was still embryonic, tight-knit, denser, and more localized, yet already organized enough to create gravitational wells deep enough to form luminous galaxies. In a way, GN-z11 is a beacon of structure in a young, volatile cosmos. It implies that the underlying dark matter filaments had already grown complex enough to funnel gas into concentrated regions. These filaments acted like galactic highways, streams of hydrogen flowing into gravitational basins where galaxies like GN-z11 could ignite. This inflow of gas not only allowed GN-z11 to form stars rapidly but may also explain why its growth seemed to defy early expectations. It was drinking deeply from a river of primordial fuel flowing through the early web. Interestingly, the existence of GN-z11 in such an early node suggests that the first galaxies were not randomly distributed, but were already following the hidden geometry of the cosmic web. These galaxies would cluster around the densest areas, meaning GN-z11 might have been surrounded by other forming galaxies, too faint or too small for us to currently detect. The idea that it may have belonged to an early protocluster, a forerunner of the vast galaxy clusters we see today, adds even more weight to its significance. Simulations of the early universe, such as those from the Illustris or Millennium projects, support this idea. They show that as early as Redshift 11, where GN-z11 resides, web-like structures were already starting to stretch across the universe, mapping out the places where matter would condense, stars would form, and galaxies would eventually collide and merge. GN-z11 represents a real, observable confirmation of these predictions. It isn't just a galaxy, it's a landmark, a pin on the map of the earliest cosmic geography. Furthermore, by locating and studying more galaxies like GN-z11, astronomers hope to trace the filamentary skeleton of the early cosmos. Each new high-redshift galaxy we find is not just an isolated point, it's part of a larger puzzle, hinting at the directions the filaments run, the distribution of matter, and the growth of structure from simplicity to complexity. GN-z11 is one of the first such puzzle pieces we've had the privilege to observe directly. And then there's the matter of voids. While GN-z11 resides in a dense region, its existence implies that vast areas around it were likely still empty, cold deserts of neutral hydrogen where galaxy formation had not yet begun or had only just flickered to life. The contrast between the dense node containing GN-z11 and the surrounding emptiness is part of what defines the cosmic web. It's not a uniform spread of galaxies, it's a patchwork of presence and absence, and GN-z11 is our first glimpse into how that contrast was already being painted into the universe. The cosmic web would eventually give rise to galaxy clusters, filaments stretching across billions of light years, and vast supervoids that baffle astronomers even today. GN-z11, with its redshift of 11.09, exists at a time when this tapestry was being woven, thread by gravitational thread. Its position within this emerging architecture tells us not just about its own story, but about the deep framework of the universe that made its story possible in the first place. So while it may be easy to imagine GN-z11 as a lonely outpost in the distant universe, the truth is far more profound. It is part of a larger, interconnected system, a node in a vast and growing web that spans the cosmos. And as we discover more galaxies from that early epoch, we're not just finding isolated dots, we're beginning to see the outlines of the universe's first great structure, a lattice of light and matter that would shape everything to come. One of the most tantalizing questions astronomers have about GN-z11 is whether such a young, compact, and fast-evolving galaxy could already harbor a supermassive black hole at its core. It seems almost paradoxical. How could something as massive and complex as a black hole, millions or even billions of times the mass of our Sun, form so early, when the universe itself was still in its infancy? Yet, time and again, observations of other ancient galaxies have revealed the presence of surprisingly massive black holes not long after the Big Bang. Could GN-z11 be another such case? The idea isn't as implausible as it once seemed. In fact, recent discoveries have increasingly shown that black holes and galaxies evolve together, often from their very beginnings. Central black holes are now believed to be almost ubiquitous in galaxies, from dwarf systems to giant ellipticals. And the correlation between the mass of a galaxy's bulge and its central black hole, the so-called M-sigma relation, suggests that even in these earliest stages of galactic development, black holes may have played a foundational role. GN-z11, although tiny compared to galaxies like the Milky Way, was undergoing intense star formation, pumping out stars at 20 solar masses per year. This kind of rapid, compact growth creates the kind of dense environments where gas can collapse very quickly, not just into stars, but potentially into black holes as well. Some theoretical models suggest that black holes can form directly from the collapse of massive gas clouds, a process called direct collapse black hole formation, without needing to go through the slower route of forming stars first, and then collapsing into stellar remnants. In such scenarios, regions within early galaxies with very high densities, low metallicity, and high inflow rates could become unstable enough to bypass star formation altogether. Instead, the gas would rapidly collapse under its own gravity into a black hole seed, possibly tens of thousands to hundreds of thousands of solar masses. Given GN-z11's highly compact nature and extreme gas accretion rate, it could very well have harbored the right conditions for such a process. But even if GN-z11 didn't start with a massive seed, there's another possibility. It might have quickly grown a black hole from stellar remnants. The massive, short-lived stars forming within GN-z11 would have exploded as supernovae after just a few million years, leaving behind stellar mass black holes. In such a dense, chaotic environment, these black holes could quickly sink toward the galactic center, merge, and begin accreting surrounding gas. If enough gas was available, and GN-z11 seems to have had plenty, it could rapidly evolve into an intermediate mass or even a supermassive black hole within tens of millions of years. Adding to the plausibility is the growing number of high-redshift quasars, bright, energetic objects powered by actively feeding supermassive black holes, discovered at redshifts greater than 7. Some of these quasars host black holes with masses over 1 billion solar masses, shining just a few hundred million years after the Big Bang. If black holes of that magnitude can exist at such early times, it stands to reason that smaller black holes, perhaps in galaxies like GN-z11, could have existed as well, quietly growing or waiting for fuel to ignite a more active phase. So far, no X-ray or radio signatures, common signs of accreting black holes, have been detected in GN-z11. But this doesn't rule out the possibility. The current data on GN-z11, based largely on Hubble's capabilities and ground-based spectroscopy, is limited in resolution and sensitivity. If GN-z11 does host a black hole, it may not be actively accreting material, or its emissions may be too faint to detect at this time. Alternatively, the accretion may be heavily obscured by gas and dust, especially in such a compact star-forming environment. With the James Webb Space Telescope, JWST, now operational, this picture could change. JWST's powerful mid-infrared instruments are designed to peer into the dusty, turbulent hearts of early galaxies like GN-z11. If a central black hole is present and feeding, even modestly, it might leave telltale signs, such as broad emission lines, hot dust signatures, or subtle distortions in spectral profiles that hint at extreme gravitational environments. And if JWST, or future instruments, does confirm a black hole in GN-z11, it would fundamentally reshape our understanding of early galactic evolution. It would show that black hole formation is not a late-stage process, but one that begins almost as soon as galaxies do. It would imply that the seeds of cosmic structure, black holes, galaxies, stars, and clusters, are intertwined from the very beginning. It would also raise provocative questions. Could black holes have played a catalytic role in the formation of early galaxies rather than just being a byproduct? Could they have helped regulate star formation through feedback, even in the first 400 million years? Or perhaps black holes themselves helped carve the earliest pathways in the cosmic web, creating overdensities that led to the birth of galaxies like GN-z11. In any case, whether GN-z11 houses a black hole or not, the very possibility pushes the boundaries of what we thought was achievable in the early universe. It reminds us that the cosmos was not hesitant or slow in building complexity. It moved swiftly, almost impatiently, to generate structures we once thought took eons to form. And within that urgency, a tiny, brilliant galaxy may have cradled one of the universe's first gravitational titans, an invisible anchor quietly shaping the destiny of the light around it. Since the discovery of GN-z11 by the Hubble Space Telescope in 2016, it held a revered status in astronomy, a record-breaking window into the young universe, the most distant and ancient galaxy ever observed at that time. But the universe, like all stories, keeps unfolding. And with the launch of the James Webb Space Telescope, JWST, a new chapter in that story has begun, one that recontextualizes GN-z11 not as the farthest boundary, but as a milestone along a rapidly expanding frontier. JWST has identified several candidate galaxies that appear to be even older, even farther away in both space and time. But rather than diminishing GN-z11's importance, these new discoveries deepen its relevance and sharpen the questions it helped us first ask. JWST's infrared eyes have allowed astronomers to push deeper into cosmic history than ever before, identifying galaxies with photometric redshifts estimated at Z equals 12, 13, even up to 16 or beyond. One of the most notable of these is CERS 93316, a galaxy that initially stunned the astronomical community by appearing to exist at a redshift of around Z equals 16.7, which would place it at just about 250 million years after the Big Bang. While that measurement is still under refinement and requires spectroscopic confirmation, even the possibility of such a galaxy shifts the boundary of the known universe outward, leaving GN-z11 no longer at the very edge, but still breathtakingly close. These JWST-discovered galaxies tend to share many of GN-z11's characteristics. They are small, compact, and astonishingly luminous for their age. Some even show signs of complex structure, hinting at surprisingly fast and early development. The parallels are striking, and they suggest that GN-z11 may not be a rare outlier, but instead part of a larger population of early, efficient galaxies that we are only now beginning to uncover. GN-z11 was the first beacon. Now we see a constellation. Yet, for all the excitement surrounding these new candidates, GN-z11 still holds a special status. Unlike most JWST discoveries to date, GN-z11 has been confirmed spectroscopically. That is, its redshift was not merely estimated based on its colors or brightness, but measured directly from the displacement of its light's spectral features, a far more robust and precise method. This makes GN-z11 a cosmic anchor, a trusted reference point against which newer, unconfirmed candidates are compared. That distinction matters. While JWST has provided us with an astonishing number of early galaxy candidates, many of them await the kind of spectroscopic verification that GN-z11 has already passed. Photometric redshifts can sometimes be misleading, affected by foreground dust, strange galaxy colors, or unexpected spectral energy distributions. Until a galaxy's redshift is confirmed with absolute confidence, it remains a candidate rather than a confirmed record breaker. Moreover, GN-z11 benefits from years of detailed follow-up and modeling. Its star formation rate, metallicity, mass, and even tentative clues about its internal structure have been carefully studied. These data make it not just a distant galaxy, but a well-characterized laboratory for early universe conditions. It provides a foundation on which JWST's new findings can be interpreted. By comparing galaxies at similar redshifts or even slightly earlier epochs to GN-z11, astronomers can begin to trace patterns in star formation rates, brightness, galaxy morphology, and elemental composition that define how galaxies emerged from the cosmic darkness. There's also the symbolic weight of GN-z11's legacy. It was, for a time, the outermost point of human reach into the past. For years, it stood alone at the edge of observation, reminding us that light could cross 13.4 billion years of time and space to reach us. It ignited the quest for deeper discovery and served as a benchmark for the technologies that followed. If GN-z11 hadn't been found and confirmed, would the astronomical community have been so emboldened to push for JWST's more aggressive observational campaigns targeting even earlier epochs? In fact, many of JWST's early programs were designed with GN-z11 in mind. It defined the zone of interest. It sharpened the tools. It justified the strategies. And now, with each new galaxy JWST detects, GN-z11 becomes more relevant, not less. It offers the chance for direct comparison. How similar are these galaxies? Are they forming stars at the same rate? Do they share metallicity profiles? Are their brightnesses comparable? And what does that mean about the universe's pace of structure formation? Perhaps most intriguingly, the emerging population of ancient galaxies, including GN-z11, hints that galaxy formation happened faster and more efficiently than once believed. Before these discoveries, many models predicted that galaxies would struggle to take shape before about 500 million years after the Big Bang. Now, with GN-z11 at 400 million years, and CRS 93316 potentially at 250 million, that boundary is being rewritten. The universe, it seems, wasted no time. It didn't gradually warm to the idea of complexity, it exploded into it. This shift challenges existing theories about the formation of the first stars, the buildup of mass in galaxies, and the role of dark matter in sculpting the cosmic web. And GN-z11, as one of the best-studied galaxies from this early time, offers critical evidence for calibrating those theories. Its presence implies that massive starbursts, metal production, and possibly even black hole formation were not only possible but already underway in the first 3% of the universe's history. So while JWST's discoveries may now exceed GN-z11 in redshift, they don't render it obsolete. They extend its story, reframing it as one point on a broader timeline. GN-z11 was the first chapter in a book that's now rapidly filling with new pages. But it's the chapter we've read most closely, the one whose details we understand well enough to use as a reference, a comparison, and a cornerstone of early galaxy research. As more JWST candidates are confirmed and the early universe map becomes clearer, GN-z11 will remain the thread that ties past observations to future revelations. It represents the moment when we first looked back far enough to glimpse the sparks of cosmic dawn, and the moment we realized there were many more still waiting to be seen. In the earliest epochs of the universe, chaos reigned, not in the way we often imagine chaos as disorder, but in the form of raw, untamed energy and unstructured matter. The cosmos had just emerged from the fireball of the Big Bang. For hundreds of thousands of years, it was an opaque sea of hot plasma, a glowing fog of particles unable to settle, where photons scattered off free electrons and nothing could travel freely. There were no stars, no galaxies, just a uniform, blinding soup of hydrogen, helium, electrons, and light trapped in a cosmic blur. But this chaos had a secret: it wasn't perfectly uniform. Quantum fluctuations, tiny ripples in density caused by the uncertain nature of particles in the infant universe, left behind slight imperfections in this otherwise smooth sea. These minute differences in density were magnified as the universe expanded. Areas just slightly denser than their surroundings began to gravitationally attract more matter. Over millions of years, these overdensities evolved into the first clouds of gas dense enough to form galaxies. After about 380,000 years, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time. The cosmic fog lifted, and the cosmic microwave background (CMB) was born, a snapshot of the universe frozen at that moment. But while this marked a transition into transparency, the universe was still dark. No stars had yet formed. The cosmos entered what we now call the Dark Ages. It was during this time that those initial density fluctuations had their moment. Gravity quietly gathered the loose hydrogen and helium, the only two elements in meaningful supply at the time, into clumps. These gas clouds began to collapse under their own weight, compressing, heating, and spinning. Inside the densest pockets, temperatures and pressures became high enough for nuclear fusion to ignite, and the first stars flickered into existence. These first stars were unlike any we see today. Composed entirely of pristine hydrogen and helium, they are believed to have been massive, hot, and short-lived, tens to hundreds of times the mass of our Sun. They burned with fierce luminosity, producing intense ultraviolet radiation and quickly exploding in violent supernovae. These explosions scattered the first heavy elements, carbon, oxygen, silicon, into the surrounding space, polluting the once pure gas and setting the stage for later generations of stars. Out of this cycle of collapse, ignition, explosion, and enrichment, the first galaxies began to take shape. But it was far from a smooth process. The gravitational tug-of-war between collapsing matter and the expanding fabric of space created an unstable environment. Clouds of gas often fragmented into multiple pieces, each competing for material. Galaxies merged frequently, their chaotic collisions triggering even more star formation and creating irregular, unstable shapes. This early era of galaxy formation, sometimes referred to as cosmic dawn, was defined by its extremes. Gas inflows were violent. Star formation was rampant. Radiation from young stars ionized the surrounding hydrogen, carving out ionized bubbles that gradually expanded and merged in a process known as reionization. This epoch, extending from roughly 400 million to 1 billion years after the Big Bang, marked the final transition of the universe from opaque to transparent, powered by the birth of the first luminous objects. Galaxies like GN-z11 were products of this primordial chaos. They did not arise in isolation or serenity. They were built in turbulence, formed from collapsing filaments of hydrogen and helium funneled along the cosmic web into nodes of gravitational instability. The gas that fed them came from vast, intergalactic flows, driven by the dark matter scaffolding that defined the universe's large-scale structure. The lack of heavy elements meant cooling mechanisms were limited. Metal-free gas doesn't radiate heat efficiently, which affects how it fragments and collapses. As a result, the first stars and galaxies formed under very different physical rules than those in today's metal-enriched universe. Their environments were hotter, their masses more extreme, their evolution faster. The gravitational interactions between young galaxies added even more chaos. With no established cosmic order, these objects crashed into each other frequently, merging and interacting in a cosmic dance that often disrupted their shapes, enhanced their star formation rates, and sent shockwaves through the interstellar medium. These mergers were not delicate unions. They were violent and transformative, redistributing gas, compressing regions into starburst cores, and sometimes triggering the formation of early black holes. And through it all, the background radiation of the universe was cooling, the large-scale structure was becoming more defined, and the balance between gravity and expansion was constantly shifting. The galaxies that managed to survive these early trials, like GN-z11, were the ones that formed quickly, efficiently, and in the right gravitational cradles. They represent the survivors of the early chaos, bright markers of a time when the universe was just beginning to self-organize from disorder into complexity. Even today, the light we see from GN-z11 carries the imprint of this chaos. Its high redshift, rapid star formation, low metallicity, and compact structure all point back to a time when the laws of astrophysics were playing out at high speed, under raw, primal conditions. Its mere existence challenges models that once assumed galaxies needed hundreds of millions of years to take form. In truth, the early universe was not peaceful. It was fast, hot, unstable, and bursting with potential. It was a laboratory where the simplest ingredients, hydrogen and helium, were violently shaped into the building blocks of everything that would follow. And from this maelstrom came the first cities of stars. GN-z11 was one of them. GN-z11's brightness is one of its most puzzling and fascinating traits. When astronomers first detected this galaxy over 13.4 billion light-years away, they expected it to be faint, barely a whisper against the dark backdrop of the early universe. After all, galaxies that existed just 400 million years after the Big Bang should, by most models, be small, dim, and starved for fuel. But GN-z11 wasn't just visible, it was surprisingly luminous. In fact, it shone far more brightly than most galaxies known at comparable epochs. That unexpected glow opened the door to a set of intriguing questions. What made GN-z11 so bright? And how could a galaxy so young generate so much light? Several theories attempt to explain this mystery, each illuminating a different aspect of what might have been happening inside this ancient object. The first, and most straightforward, is that GN-z11 was undergoing an intense burst of star formation. Star formation generates light, especially when it involves the formation of massive, short-lived stars that burn hot and radiate intensely in the ultraviolet. Data indicates GN-z11 was forming stars at a rate of approximately 20 solar masses per year. For a galaxy only a fraction of the size of the Milky Way, this is a stunningly high rate. It's as though GN-z11 was burning fuel as fast as it could, lighting up its environment in the process. But even that level of star formation doesn't completely explain the level of brightness GN-z11 exhibits. For a galaxy that early, other mechanisms might be at work too. One hypothesis involves stellar populations with unusual properties, specifically stars that belong to the so-called population 3 category. These would be the universe's first stars, formed from pristine hydrogen and helium, with virtually no heavier elements, what astronomers call metals. Population 3 stars are predicted to be far more massive and hotter than later generations, sometimes reaching hundreds of times the mass of our Sun. These stars would live fast and die young, but during their brief lives, they would shine extraordinarily brightly, especially in the ultraviolet. If GN-z11 harbored a significant population of such stars, their combined output could easily contribute to the galaxy's unexpected brightness. Another possibility is low dust content. Dust absorbs and scatters ultraviolet and visible light, dimming a galaxy's appearance from our point of view. But GN-z11's light seems to reach us with minimal attenuation. That suggests the galaxy has very little dust, a natural consequence of its youth. Dust forms over time as stars evolve and die, releasing elements like carbon, silicon, and oxygen into the interstellar medium. In a galaxy just a few 100 million years old, there simply hasn't been enough time for much of that process to occur. So the starlight escapes relatively unfiltered, and we see the galaxy in its raw, blazing intensity. Then there's the question of galactic structure. GN-z11 appears to be extremely compact, meaning its stars and gas are packed into a relatively small region of space. This concentration could enhance its surface brightness, essentially the brightness per unit area, making it easier to detect across vast distances. If GN-z11 formed in a gravitational well at the intersection of cosmic filaments, it might have benefited from a steady flow of cold gas, funneled into its core where it could rapidly form stars. This cold accretion model would provide both the fuel and the conditions needed for a compact starburst galaxy. Some astronomers have even speculated that GN-z11 might host a hidden black hole, potentially an actively feeding one. While there's no direct evidence of this yet, no X-rays, no telltale emission lines, the possibility remains intriguing. A small but fast-growing black hole in the center of the galaxy could add an extra layer of energy, heating gas and producing light across multiple wavelengths. Even if the black hole itself were not actively accreting at the time we observe it, its presence could have triggered or regulated star formation in the past, shaping the galaxy's overall brightness profile. Another factor to consider is the effect of gravitational lensing, the bending and magnifying of light by massive foreground objects like galaxies or clusters. Lensing can dramatically amplify the brightness of distant galaxies. However, in the case of GN-z11, this has largely been ruled out. Its position in the sky and the absence of any massive intervening object make it unlikely that lensing is responsible for the observed luminosity. That only strengthens the conclusion that GN-z11 is intrinsically bright, not artificially magnified. It's also possible that we're witnessing GN-z11 during a short-lived peak phase in its life cycle. Galaxies are not static. They go through bursts and lulls in activity. We may have caught GN-z11 at a moment of particularly intense star-forming activity, just before a potential slowdown. This kind of variability could explain the brightness, especially if the burst was triggered by a merger with a smaller gas-rich companion, or a sudden influx of pristine gas from the cosmic web. And then there's the final, sobering possibility. Perhaps our models of early galaxy evolution are still incomplete. GN-z11 and galaxies like it challenge the assumptions of gradual, bottom-up growth, where small structures slowly merge to become larger ones over time. Instead, GN-z11 suggests that some galaxies formed rapidly and efficiently, assembling mass and igniting star formation far earlier than we thought possible. It implies that the early universe was a more dynamic, more productive environment than many theories had anticipated. In the end, GN-z11's brightness isn't just a physical trait, it's a clue. A beacon. A signal from the early cosmos that says, "Look again. There's more happening here than you think." Whether powered by dense star formation, primordial stars, a lack of dust, or deeper unknowns, its luminosity continues to provoke questions about what the early universe was capable of. It's a reminder that the cosmos doesn't always follow our expectations. Sometimes it outshines them. The question of whether GN-z11 formed in isolation or was part of a small community of galaxies is far more than a matter of cosmic geography. It gets to the heart of how structure formed in the early universe. If GN-z11 had companions, neighbors, satellites, or clustered peers, it would suggest that galaxy formation was already a social process just a few 100 million years after the Big Bang. If it was alone, then it might represent a rare exception, a solitary beacon rising out of darkness against a quiet cosmic backdrop. The truth is, we don't yet know for sure, but the evidence is leaning towards something far more intricate than isolation. To understand why, we have to revisit the context of GN-z11's birth. Galaxies don't simply pop into existence out of nowhere. They condense from the densest parts of the cosmic web, gravitationally drawing gas and matter from surrounding space. These regions of increased density, called overdensities, are fertile grounds for galaxy formation. And the higher the density, the more likely it is that multiple galaxies will form in close proximity. That's the cosmic version of a neighborhood. If GN-z11 formed in such a region, it's entirely plausible that other galaxies were forming nearby, fed by the same web of cold gas and dark matter scaffolding. In fact, some models suggest that the first galaxies often formed in protoclusters, early versions of the massive galaxy clusters we see in the modern universe. These protoclusters would be small by today's standards but dense enough to seed multiple star-forming systems within a few 100,000 light-years of each other. So if GN-z11 had neighbors, why haven't we seen them? The most obvious answer is, they might be too faint to detect with current instruments. While GN-z11 is unusually bright and compact, any smaller or more diffuse companions would be incredibly difficult to observe, especially given the immense distance involved. The light from these galaxies would be not only faint but highly redshifted, potentially falling outside the sensitivity range of the instruments we've been using until recently. Even with JWST, which offers dramatically improved resolution and sensitivity in the infrared, detecting companions to GN-z11 remains a challenge. The galaxy lies at the very edge of what we can currently resolve, and distinguishing faint, nearby structures from noise or background objects is still an evolving skill set. But some initial observations from similar galaxies have found small overdensities, hints of fainter galaxies clustered near known high redshift ones. These might be the embryonic building blocks of galactic groups or clusters, all forming together from the same pool of early matter. Another possibility is that GN-z11 did have companions but has since merged with them. Mergers were incredibly common in the early universe, as galaxies constantly collided and combined to grow in mass and complexity. These collisions weren't the slow dances we sometimes see in modern galaxies. More often they were fast, chaotic, and transformative. If GN-z11 had small neighbors early on, it may have absorbed them in a series of rapid mergers, which could explain its surprising brightness and rapid star formation. In this scenario, GN-z11 may be the surviving core of what was once a group of tiny, fledgling galaxies. Of course, we can't rule out the opposite either, that GN-z11 was, at least temporarily, alone. Even in an evolving universe filled with forming galaxies, there would have been voids and low-density regions, places where galaxy formation lagged behind. GN-z11 might have emerged in such a place, driven by a rare alignment of favorable conditions, a dense local pocket of gas, a cooling halo of dark matter, and just the right instabilities to ignite star formation. If so, it would be one of the first galaxies in its region, perhaps blazing the trail for others that would form millions of years later, seeded by the metals and radiation GN-z11 expelled into its surroundings. If it was isolated, that makes GN-z11 even more remarkable. It would mean the galaxy was able to gather gas, form stars rapidly, and shine across billions of light years, all without the benefit of a surrounding cluster of fellow galaxies to interact with or draw material from. It would stand as a kind of cosmic pioneer, shaping its corner of the universe alone. However, many cosmologists lean toward the idea that GN-z11 was not truly isolated, but rather part of a larger, hidden system. It's likely that there are smaller, dimmer galaxies in its vicinity that simply haven't yet been detected. With the increasing observational power of JWST and future instruments like the Nancy Grace Roman Space Telescope, we may soon be able to probe the region around GN-z11 in exquisite detail. This could reveal not only neighboring galaxies but also the structure of the local dark matter halo, gas filaments, and possibly even faint signs of protocluster assembly. The implications of GN-z11 having neighbors are profound. It would suggest that galactic ecosystems were already forming when the universe was just 3% of its current age. That galaxies influenced each other through gravity, radiation, and feedback loops even in these early stages. That the first cosmic structures weren't scattered, isolated lights, but were connected, evolving in groups and beginning the long process of cosmic networking that would eventually create the vast clusters and superclusters we observe today. In the grand scheme of the universe's history, this question, was GN-z11 alone, touches on the very mechanisms of how the cosmos built its first architecture. Whether alone or accompanied, GN-z11 reminds us that the early universe was already rich with drama, complexity, and the kinds of questions that keep astronomers peering deeper into the past. GN-z11 doesn't just sit at the edge of the known universe, it defines it. At the time of its discovery, it marked the furthest reach of human vision into the past, a staggering 13.4 billion light-years away. When we observe GN-z11, we're not just seeing a distant galaxy, we're seeing what is perhaps the upper limit of what a telescope like Hubble was capable of perceiving. In many ways, GN-z11 isn't merely a galaxy, it's a boundary, a milestone, a stress test for observational astronomy. And the natural question that follows from standing at such a limit is, could we go further? To answer that, we first need to understand the concept of a cosmic horizon, not just in space, but in time. The universe is about 13.8 billion years old, but due to the expansion of space itself, the most distant objects we can observe today lie much farther than 13.8 billion light-years away. Their light began traveling toward us billions of years ago, but the space between has stretched so much that those galaxies are now about 33 billion light-years away in present-day distance. Yet we can only detect what has had time for its light to reach us. That defines our observable universe, and within it, the ability to detect objects from earlier and earlier epochs becomes exponentially more difficult. GN-z11's redshift of 11.09 places it only about 400 million years after the Big Bang. This is extraordinarily close to the cosmic beginning, leaving just a narrow sliver of time, perhaps 100 to 200 million years, for any earlier galaxies to exist. So if we want to look further, we're essentially trying to pierce through that final veil, to glimpse the very first structures, the earliest flickers of starlight that broke the cosmic dark ages. Hubble pushed to the edge of its capabilities to detect GN-z11. The faint light of such a distant object is extremely redshifted, meaning it's stretched by the expansion of space until it moves out of the visible range and into the infrared. Hubble could barely touch this range, and even then, only with deep, concentrated exposures that took hundreds of hours. GN-z11 was detected as a small, faint smudge, but one with enough brightness and shape to stand out. Yet beyond GN-z11, Hubble simply could not see. The light was too red, the galaxies too faint, and the universe too distant. We had reached the observational cliff. Then came the James Webb Space Telescope. JWST was designed specifically to answer the question GN-z11 poses: what lies beyond? With its massive, gold-coated mirror and its sensors optimized for the infrared, JWST can detect redshifted light from the very first stars and galaxies, objects that formed just 200 million years or less after the Big Bang. Already in its first surveys, JWST has detected candidates at redshifts of 12, 13, 14, even possibly above 16. These are galaxies that may predate GN-z11 by 100 million years or more. We are beginning to see past GN-z11, not just in theory, but in practice. And yet, GN-z11 still matters deeply. Because it was discovered and confirmed through spectroscopy, not just inferred from color like many JWST candidates, it remains one of the most secure observations of the early universe. It tells us not only what a galaxy at this distance looks like, but what it behaves like, what it contains, and how it evolves. It's a calibration point, a cosmic standard candle for this epoch. And the farther we try to look, the more important such reliable benchmarks become. Could we see even further than JWST allows? Theoretically, yes. There is still light from even earlier times, perhaps from the first generation of stars, the so-called population 3 stars, that is reaching us. But these stars were likely short-lived, isolated, and low in overall brightness. Detecting them individually may be impossible with today's tools. Even JWST, powerful as it is, might not be sensitive enough to catch the fleeting signatures of single first-generation stars unless they are magnified by gravitational lensing, boosted by the gravity of massive intervening objects. But that's not the end of the road. Future telescopes like the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, ELT, and proposed concepts like the LUVOIR or Origins Space Telescope could combine even larger mirrors, more advanced sensors, and longer observing times to take us deeper still. These instruments may one day resolve entire protogalaxies in the process of forming, clouds of hydrogen collapsing before the first stars ignite. They might detect the reionization bubbles around the first starlight, or measure the intergalactic medium before it was transformed by galactic feedback. Still, as we push further, the challenges multiply. The light is weaker. The objects are smaller. The signals are buried in noise. And the risk of false positives increases. That's why GN-z11 continues to matter. It's one of the few truly confirmed objects near the cosmic dawn. Every time we detect something new, we ask, how does it compare to GN-z11? Is it brighter? Fainter? More massive? Does it share similar chemistry? Without confirmed guideposts like GN-z11, we would be walking blindly into the dark. In some sense, GN-z11 defines the visible boundary of the past, not in absolute terms, but in practical ones. It marks a moment when light, gravity, and matter conspired to send a message across time. Its photons left when the universe was less than 3% of its current age, traveling uninterrupted through expanding space, past forming galaxies, past uncounted voids, and finally into our telescopes. And now, standing on that edge, we look further still, not just because we can, but because GN-z11 showed us that we should. Beyond GN-z11, the universe continues to astonish. When GN-z11 was first confirmed, its redshift of 11.09 placed it firmly as the most distant and earliest known galaxy ever detected. It seemed we had reached a cosmic milestone, a deep space frontier that would stand for years. And it did, until the James Webb Space Telescope, JWST, with its powerful infrared vision, began its voyage into the abyss. Suddenly, the darkness beyond GN-z11 started to flicker with unexpected light. Among the most striking discoveries is CERS 93316, a galaxy candidate detected during the Cosmic Evolution Early Release Science (CERS) survey with JWST. Preliminary analysis suggested an astonishing photometric redshift of Z is almost equal to 16.7, which, if confirmed spectroscopically, would place this galaxy a mere 250 million years after the Big Bang. That's 150 million years older than GN-z11, pushing the window of galaxy formation far closer to the cosmic beginning than we had previously imagined possible. And CERS 93316 isn't alone. Other JWST surveys like GLASS, JADES, and Panoramic have revealed a growing list of ultra-high redshift candidates, some estimated around Z equals 13 to 15, including GLASS Z13 and JADES GS-Z13-0, each hovering in that mystical epoch when the very first light began reshaping the cosmos. These galaxies are faint, small, and often extremely redshifted, appearing more like glowing embers than structured galaxies. But they carry a simple message: galaxies were already forming earlier than we expected. However, these newer discoveries do not erase GN-z11's legacy, they build upon it. GN-z11 remains the first high redshift galaxy with robust spectroscopic confirmation, which is a major distinction. Most of the galaxies detected by JWST so far are identified using photometric redshifts, analyzing the brightness of the galaxy in different filters and estimating its distance from its color profile. While this technique is powerful, it's not foolproof. Dust, odd star populations, or other galaxies along the line of sight can sometimes create redshift illusions. Spectroscopy, on the other hand, reads the fine details of a galaxy's light, its spectral lines, shifting them to calculate distance with much higher confidence. GN-z11's redshift of 11.09 is not an estimate. It's a measured reality, confirmed by the precise stretching of emission lines like Lyman alpha. This gives it a bedrock status in high redshift astronomy, a kind of cosmic calibration standard that newer candidates are compared against. And GN-z11 is not just remarkable for how far it is, but also how much we've learned from it. Its brightness, structure, star formation rate, and metallicity have been scrutinized and modeled in detail. It has taught us that galaxies can form quickly, that they can burn bright even in the early void, and that the conditions of the young universe may have been more dynamic and creative than our models once allowed. It raised new questions, sharpened existing theories, and challenged assumptions that galaxy formation was a slow, delayed process. In a sense, GN-z11 didn't just push the boundary of what was visible, it expanded the conceptual framework for what we considered possible. It showed us that cosmic dawn may have begun earlier, and in a more vigorous way, than we had dared imagine. Every new candidate found by JWST adds to this evolving story, but GN-z11 remains the narrative anchor, the point of reference that validated the journey into deeper darkness. And perhaps most critically, GN-z11's discovery paved the path that JWST now walks. Its confirmation gave astronomers the motivation and confidence to design observational programs specifically targeting galaxies of similar or even greater redshifts. Without GN-z11, the scientific community might not have been as aggressive in probing the Z greater than 10 realm. In this way, GN-z11 is not just a destination, it's a launching point. It also serves as a crucial touchstone for understanding how galaxies evolve across time. With new candidates stretching even further back, astronomers can now begin to build a timeline of early galaxy growth. By comparing GN-z11 with CERS 93316 or GLASS Z13, they can trace how star formation rates, metallicity, brightness, and structure change with each step closer to the Big Bang. GN-z11 is the midpoint on this rapidly emerging map, older than most, younger than a few, but more fully understood than nearly any other at its epoch. As future telescopes come online and spectroscopic follow-ups confirm, or revise, these JWST redshift estimates, GN-z11 will remain central. It is the bridge between eras, between what Hubble could barely glimpse and what JWST now boldly uncovers. And even if it loses its record for distance, it has already claimed a far more enduring one, for being the first galaxy to show us, undeniably, just how deep we could peer into time. When we talk about cosmic dawn, we're not speaking metaphorically. It is quite literally the time in the universe's history when the first light of stars and galaxies began to shine, lifting the cosmic fog and transforming the darkness into a universe illuminated by structure, complexity, and energy. Before this moment, the cosmos was quiet and dark. The universe had cooled after the Big Bang, hydrogen atoms had formed, and the sky was filled only with a cold, neutral gas. There were no galaxies, no stars, no planets, nothing but a vast, dark expanse. But then something remarkable began to happen. The universe began to glow from within. This epoch, cosmic dawn, is incredibly hard to observe directly. The first stars and galaxies were small, dim, and distant, and the light they emitted was stretched across billions of years to such long wavelengths that detecting it requires extremely sensitive instruments. And this is exactly why GN-z11 is so important. It is not just a distant galaxy. It is a map point within cosmic dawn itself, a signal from one of the earliest known luminous objects ever observed. By existing at just 400 million years after the Big Bang, GN-z11 sits right at the edge of when the universe began transitioning from darkness into light. That light wasn't instant. It didn't switch on like flipping a cosmic switch. It happened gradually, over hundreds of millions of years. As stars formed, galaxies assembled, and radiation escaped to ionize the surrounding hydrogen gas. Observing GN-z11 gives us direct insight into that transitional time, a piece of the puzzle of how and when the universe lit up. Every galaxy detected at extreme redshift helps us define the timeline of this dawn, but GN-z11 is special because of what we know about it. It's bright, forming stars rapidly, and actively shaping its environment. That tells us that by 400 million years post-Big Bang, not only had galaxy formation begun, it was well underway. The conditions necessary to form stars, create internal structure, and emit intense radiation were already present. GN-z11, in essence, proves that the cosmic light switch had already been flipped, at least partially. By mapping galaxies like GN-z11 across redshift, we are essentially mapping time. And when we place GN-z11 on this temporal map, it shows us a universe that is no longer static and dark, but one that is forming stars, generating energy, and beginning to carve out the scaffolding of all future structure. It helps define the front edge of reionization, the process where ultraviolet light from young stars and galaxies ionize the surrounding hydrogen gas, making the universe transparent to light again. But GN-z11 does more than simply mark a position. Its physical characteristics, like its brightness, its size, its star formation rate, and its metallicity, help contextualize the other, even more distant galaxy candidates found since. When we observe something at redshift 13 or 16, those are merely candidates until we understand how galaxies behave at these epochs. GN-z11 gives us a real, confirmed data point against which to test our assumptions. Is a galaxy at Z equals 13 brighter or fainter than GN-z11? Is it larger or smaller? Does it seem older or less evolved? Without GN-z11, these comparisons are far less meaningful. Moreover, GN-z11's existence indicates that the process of galaxy formation may have started even earlier than we previously assumed. If such a bright, rapidly evolving galaxy already exists at Z equals 11, that means its formative stages began even earlier, perhaps 100 million years prior. This pushes our estimations for the very beginning of cosmic dawn closer and closer to the Big Bang itself. In recent years, cosmic dawn has become one of the most important frontiers in astrophysics. Researchers are not just interested in finding early galaxies. They want to understand how they formed, what they were made of, and how much they influenced their surroundings. GN-z11, with its uniquely clear signal and detailed study, is a cornerstone in that effort. It provides a baseline, something concrete in a sea of uncertainty. As new data pours in from JWST and future observatories, we'll likely discover hundreds of galaxies that existed during or before GN-z11's time. But GN-z11 will always hold the title of one of the first clear voices from the dawn. It speaks to us from a time when darkness still blanketed the universe, but light was breaking through. It helps sketch the edge of the unknown and serves as a reminder that even in the earliest times, the universe was already beginning to tell its story in light. To understand the full impact of GN-z11 on our cosmic understanding, we must look not only at the light it emits, but at the effect that light had on the universe around it. One of the most pivotal transitions in cosmic history is the epoch of reionization, a time when the opaque, neutral hydrogen that filled the cosmos after the Big Bang was re-energized and ionized by the first sources of starlight. GN-z11, glowing just 400 million years after the beginning, offers a rare and powerful window into this mysterious phase change. Reionization marked the universe's second great transformation. The first was recombination, when protons and electrons cooled enough to form neutral hydrogen atoms and the universe became transparent for the first time, releasing the cosmic microwave background (CMB) radiation. But once that happened, the universe went dark again. There were no stars, no galaxies, no luminous structures. Just a cold, dense fog of neutral hydrogen stretching endlessly in every direction. Then, slowly, gravity pulled gas together into the first stars and galaxies. As these structures ignited, they began producing immense amounts of ultraviolet radiation, especially the hot, young stars formed in galaxies like GN-z11. These photons had enough energy to ionize hydrogen atoms, ripping apart electrons from protons and turning opaque gas into a plasma that allowed light to travel freely once again. But this process didn't happen instantly. It unfolded across hundreds of millions of years, starting with small, isolated pockets of ionized hydrogen surrounding the first galaxies. Over time, as more stars formed, these bubbles grew larger and began to overlap, eventually percolating through the entire universe. This is what we refer to as reionization, and it represents the last major, fog-lifting, event in the universe's early history. It marked the moment when starlight won the battle against darkness, and galaxies like GN-z11 were the soldiers on the front lines. The contribution of GN-z11 to this process is critical because it demonstrates that by just 400 million years after the Big Bang, galaxies were already producing enough high-energy light to participate in reionizing the cosmos. Its brightness, intense star formation, and low dust content all suggest it was a prolific source of ionizing photons. In fact, it's very likely that galaxies like GN-z11, compact, energetic, and numerous, were the primary drivers of the reionization era. Larger, brighter galaxies were rare in the early universe. But small, faint, rapidly forming galaxies like GN-z11 may have existed in greater numbers than we can currently detect. Even if each one contributed only a modest number of ionizing photons, the cumulative effect of hundreds of thousands of such galaxies could have transformed the entire intergalactic medium from neutral to ionized. Moreover, the study of GN-z11 helps us address one of the central challenges of understanding reionization, determining the escape fraction of ionizing photons. That is, how many of the high-energy ultraviolet photons produced by young stars actually make it out of the galaxy and into intergalactic space. Dust and gas can absorb or scatter these photons, reducing their impact. But GN-z11 appears to have very low dust content, and its compact size might mean that more of its radiation could escape into the void. If this is typical of early galaxies, then it supports the theory that galaxies were the dominant reionizers, as opposed to quasars or other exotic sources. Spectroscopic studies of GN-z11's light, particularly the presence and shape of the Lyman alpha emission line, also provide clues about the state of the surrounding hydrogen. This line is easily absorbed by neutral hydrogen, so its visibility suggests that at least some of the space around GN-z11 had already been ionized. This tells us something profound. GN-z11 might have carved out its own ionized bubble, a local region where starlight had already banished the darkness. It was not just a passive participant in reionization, it was an active agent shaping its environment. When astronomers stack these kinds of observations across multiple galaxies at similar and higher redshifts, they begin to map the progress of reionization, when it started, how fast it progressed, and which galaxies contributed the most. GN-z11 acts as an anchor point in that map, a tangible proof that reionization was well underway by 400 million years after the Big Bang. And there's a deeper philosophical implication here as well. Reionization is the story of the universe becoming transparent to its own light. It's the transition from a cosmos that was shrouded in darkness to one that could be seen, traversed, and eventually studied. GN-z11, shining from this transformative moment, symbolizes the birth of cosmic visibility, a time when light began to move freely, when galaxies were no longer hidden, and when the seeds of modern structure truly began to flourish. The photons we detect from GN-z11 today have traveled not just across space, but across this boundary, from a time when the universe was opaque to one when it was clear. Its light is not only ancient, it's emblematic of one of the greatest transitions in the history of everything. Through GN-z11, we aren't just looking at a distant object. We're watching the dawn of the transparent universe, and witnessing the first flickers of illumination that made the cosmos visible for all time to come. The story of GN-z11 isn't just about the galaxy. It's also about the remarkable technology that allowed us to see it. Because GN-z11 is unimaginably far away and existed when the universe was only about 400 million years old, detecting it required peering across a gulf of time and space so vast that the light we receive from it has been traveling for over 13.4 billion years. That light has been stretched by the expansion of the universe, its wavelength elongated until it's no longer visible to the human eye. It arrives at Earth as infrared radiation, faint, elusive, and difficult to detect. To find it, astronomers needed a telescope capable of catching whispers from the ancient cosmos. And that telescope was the Hubble Space Telescope. Launched in 1990, Hubble was not originally designed to hunt galaxies at the edge of the observable universe. But over the decades, its capabilities were extended, upgraded, and refined, particularly through the addition of advanced instruments that opened up the near-infrared part of the spectrum, exactly the range needed to detect galaxies like GN-z11. The key instrument in this case was the Wide Field Camera 3, WFC3, installed during Hubble's final servicing mission in 2009. WFC3 was revolutionary for several reasons. First, it offered high-resolution imaging across a broad range of wavelengths, including the near-infrared region that is essential for studying extremely redshifted galaxies. Second, it came equipped with a set of specially designed filters, each allowing only certain bands of light through. By observing the same region of the sky through multiple filters, astronomers could build a detailed picture of how bright an object is at different wavelengths, and from there, estimate its redshift. This method is called photometric redshift estimation, and it played a central role in the initial detection of GN-z11. When astronomers studied deep images of the sky, such as those from the Candel's Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, and GOOD's Great Observatory's Origins Deep Survey programs, they found a tiny, faint speck that only appeared in the reddest filters. It was invisible in the ultraviolet and visible bands, meaning its light must have been shifted so far into the infrared that it could only be captured by the deepest, most sensitive filters Hubble had. This technique, often referred to as the Lyman break technique, is based on the idea that high redshift galaxies will drop out, or disappear, in certain filters due to absorption by neutral hydrogen in the early universe. GN-z11's disappearance from bluer bands and appearance in redder ones marked it as a strong high redshift candidate. Its profile was unlike anything nearby. It didn't match the color of a dust-obscured or red star. It was something older. Something farther. Something primeval. But photometry alone wasn't enough. To confirm GN-z11's distance, astronomers turned to spectroscopy. In 2016, an international team led by Peter Oesch and Pascal Oesch used Hubble's WFC3 in GRISM mode, which allows it to function as a low-resolution spectrograph. A GRISM is a combination of a prism and a diffraction grating, used to disperse light into a spectrum. While not as powerful as ground-based spectrographs like those on the Keck telescopes, Hubble's GRISM mode has one enormous advantage: it's above the atmosphere, where there is no airglow, no water vapor, and no distortion, just a clear view of space. Using this mode, the team was able to detect a faint but unmistakable Lyman alpha break, a sharp drop in the galaxy's spectrum caused by hydrogen absorption, which directly correlates with redshift. From this, they measured a spectroscopic redshift of Z equals 11.09, making GN-z11 the most distant confirmed galaxy at the time. It was not just a fuzzy candidate. It was real. And we had seen it. All of this was made possible thanks to the deep field imaging strategy employed by Hubble. Instead of scanning wide swaths of the sky for nearby objects, Hubble was pointed at small, seemingly empty patches of sky for long durations, sometimes up to 100 hours or more, allowing the faintest, most ancient galaxies to emerge from the blackness. These ultra-deep fields, like the Hubble Ultra Deep Field, HUDF, and the Candels/Goods fields, became the hunting grounds for the first galaxies. And GN-z11 was one of their greatest treasures. It's also important to understand the immense data processing and modeling effort that accompanies these observations. Detecting GN-z11 was not as simple as spotting a bright dot and labeling it. It required meticulous analysis, rejection of false positives, careful calibration against known objects, and comparison to theoretical models. It involved removing noise, correcting for lens distortions, and isolating the signal from other sources. It demanded the use of powerful algorithms, supercomputing clusters, and years of expertise in high redshift astronomy. And while Hubble made the discovery possible, it also laid the foundation for the next generation of observations. GN-z11 pushed the limits of what Hubble could do, but in doing so, it inspired the mission goals and instrumental design of the James Webb Space Telescope. JWST is essentially Hubble's successor in the infrared, a telescope built to take the techniques that revealed GN-z11 and apply them with 10 times the sensitivity, a larger mirror, and a broader wavelength range. Instruments like NIRCam, NIRSpec, and MIRI on board JWST are direct descendants of the legacy GN-z11 helped build. So when we look at the faint, red light of GN-z11, we're not just seeing the universe as it once was. We're seeing the result of 3 decades of technological innovation, global collaboration, and human ingenuity. The detectors, filters, deep field strategies, and spectroscopic techniques that made it visible are marvels of engineering. They were designed not just to see light, but to understand it, to translate photons into knowledge, into maps, into cosmic history. GN-z11 may be ancient, but the tools that brought its light to us are modern miracles. They remind us that to touch the distant past, we must build the future. And in doing so, we extend not just our vision, but our presence, reaching across time, across space, toward the very edge of the beginning. The discovery of GN-z11 was more than a quiet observation. It was a spark that ignited one of the most exciting races in modern astronomy, the quest to find the first galaxies ever formed. When GN-z11 was spectroscopically confirmed at a redshift of 11.09, it immediately became the farthest confirmed galaxy ever observed, pushing the cosmic frontier further than ever before. It wasn't just a record holder, it was a challenge. An invitation. A line in the sand daring astronomers and telescopes to look even deeper, to go even further back, to witness light born just moments after the universe itself. For years, GN-z11 held that record, proudly standing as the most ancient light confirmed with spectroscopy. But science is never content with a single milestone. The moment GN-z11 was published in 2016, astronomers began crafting ever more sophisticated models, designing new telescopes, and refining their techniques, all aimed at one simple goal: to find what came before. But reaching further than GN-z11 isn't easy. It requires navigating the outer limits of technology, physics, and cosmic history all at once. Because of the redshift distance relationship, where light from more distant galaxies is stretched into the infrared by the expansion of space, objects older than GN-z11 emit light that is nearly invisible to most Earth-bound telescopes. Their photons are feeble, rare, and redshifted beyond what traditional instruments can detect. So the tools had to change. The methods had to evolve. And the competition began to heat up. Early attempts to find galaxies at redshifts higher than 11 used the Hubble Space Telescope in its deepest infrared exposures. Hubble's frontier fields campaign, for instance, took advantage of gravitational lensing, using the gravity of massive galaxy clusters as natural magnifying glasses to peer at background galaxies too faint to see otherwise. These fields offered glimpses of potential ultra-high redshift candidates, but without spectroscopic confirmation, they remained tentative. In parallel, large ground-based telescopes like Keck VLT, Very Large Telescope, and Subaru were also used to scour the sky for early galaxies. While these observatories are powerful, they're limited by Earth's atmosphere, which blocks most infrared light and introduces distortions. Observing at the faint levels required to beat GN-z11's record proved challenging, and no confirmed candidate emerged from this avenue that could dethrone it. That all changed with the launch of the James Webb Space Telescope in December 2021. Unlike its predecessors, JWST was built specifically to peer into the depths of the early universe. Its enormous 6.5-meter mirror collects more light than Hubble's 2.4-meter mirror, and it is optimized for the near and mid-infrared spectrum, perfect for detecting galaxies at redshifts greater than 10. Almost immediately, JWST began returning spectacular data. Within the first few months of operation, a flood of high redshift galaxy candidates were reported by excited teams around the world. One of the earliest and most headline-grabbing was GN-z11, a galaxy candidate estimated to exist at redshift Z is almost equal to 13.1, or just 300 million years after the Big Bang. Another was CERS 93316, identified at a potential Z is almost equal to 16.7, which would push the cosmic clock back to just 240 million years after the beginning, a mere blink after the first hydrogen atoms formed. These new candidates stunned the astronomical community. Not only were they possibly older than GN-z11, but they were also unexpectedly bright. According to most models, galaxies shouldn't be that luminous so soon after the Big Bang. Yet there they were, shining across space, their light taking longer to reach us than the Earth has existed by more than 2,000 times over. The implications were enormous. If galaxies were forming this early and this brightly, our understanding of galaxy formation would need to be revised, expanded, or reimagined altogether. But here's the catch. Most of these candidates were identified photometrically, not spectroscopically. That means their redshifts were inferred from their colors and brightness across multiple filters, not directly measured by examining the shift in spectral lines. While this method is powerful and often accurate, it's also vulnerable to confounding factors. Some dusty, nearby galaxies can mimic the light profiles of distant ones. Certain types of stars, like brown dwarfs, can fool even sophisticated algorithms. And gravitational lensing can distort light from more than one object, blending their signals. This is where GN-z11 continues to stand apart. Its redshift wasn't just inferred, it was measured. Its spectral fingerprint was caught directly by Hubble's GRISM mode, locking its position in time with certainty. So while JWST has found compelling candidates that seem to exist earlier, none of them had yet achieved the gold standard of spectroscopic confirmation that GN-z11 had, at least not initially. That's why the race to beat GN-z11's record is more than just about distance. It's about certainty, about validation, about rigorously proving that a galaxy is truly what it appears to be. And so, even as photometric redshift candidates flooded the literature, teams began scheduling spectroscopic follow-up observations with JWST's NIR spec, near-infrared spectrograph, designed specifically to measure redshifts with unmatched precision. These follow-ups have started bearing fruit. In 2023 and 2024, some of the early JWST candidates were confirmed to be not as distant as initially thought, revised to lower redshifts after closer inspection. Others, however, held up under scrutiny. Finally, spectroscopic confirmations began arriving for galaxies beyond Z=13, marking the true start of the new high redshift era. Still, the journey is far from over. The competition continues. With every new observing cycle, teams around the world compete for telescope time, publish preprints, and race to confirm who has truly found the earliest galaxy. Every data release is combed over by theorists, modelers, and rival research groups, each eager to confirm or challenge the findings. The race to dethrone GN-z11 is alive and thriving. Yet throughout all of this, the legacy of GN-z11 remains undiminished. It was the first to truly break the barrier, to show that galaxies could form so early and be detected across such vast time. It provided the observational proof of concept that such records could even be broken. Its existence helped shape the observing strategies, target selection, and redshift validation methods used today. It's not just a runner in the race, it was the one that fired the starting pistol. And as we move forward, the nature of the race itself is evolving. It's no longer just about finding the farthest galaxy, as if that were a static prize. It's about constructing an entire timeline of galaxy formation, about connecting the earliest light to the complex structures we see today. Each new record holder adds another link in that chain. Each confirmed galaxy paints a clearer picture of how matter, light, and structure emerged from the primordial chaos. In this grand relay across cosmic time, GN-z11 was an essential baton passed from the age of Hubble to the era of JWST. It represents a moment when the universe whispered something profound, and for the first time, we had the tools to hear it. Future galaxies may be older, further, or stranger. But none will take away the impact GN-z11 had in proving that such frontiers could be reached. The light from GN-z11 is precious. Not just because it is ancient, though it is, but because it is fragile in every sense. The photons that have traveled more than 13.4 billion years to reach our detectors are survivors. Survivors of time, space, chaos, and the natural decay of information that occurs over incomprehensible distances. Observing them is like trying to catch the whisper of a voice spoken at the dawn of time, muffled by the cosmic wind and distorted by the expansion of the universe itself. And that whisper is all we get. No second chances. No replays. Just a stream of photons, faint, stretched, and rare, arriving one by one, across the abyss. What makes this evidence so fragile is that it is not just dim, it's pushed to the extreme edge of what our instruments can detect. The further back we look in time, the more redshifted the light becomes. For GN-z11, its original ultraviolet and visible light, emitted by hot young stars, has been shifted deep into the infrared spectrum. Most of this light doesn't even make it through Earth's atmosphere, which is why we need space telescopes like Hubble and JWST to observe it. But even those orbiting observatories face challenges, because we are chasing the last remaining signatures from the earliest moments of cosmic history, signatures that are continually degraded by the processes of nature and physics. Every photon we detect from GN-z11 has been altered by the expansion of space, which stretches wavelengths and diminishes energy. The surface brightness, the amount of light received per unit area, diminishes drastically with redshift, making galaxies like GN-z11 appear not just faint, but nearly undetectable. This is a fundamental limitation of the universe's geometry, something no technological advancement can fully overcome. It's not just that GN-z11 is far, it's that it is cosmologically hidden, buried in the red mist of the universe's earliest phase. And even when we do manage to collect these precious photons, interpreting them presents another challenge. The spectral lines used to determine redshift, such as the Lyman alpha break, can be obscured, weakened, or altered by the intergalactic medium. Neutral hydrogen, still abundant in the early universe, absorbs ultraviolet light and leaves gaps in a galaxy's spectrum. This is both a blessing and a curse. It helps us identify ancient objects through the Lyman break technique, but it also removes data we might otherwise use to study a galaxy's composition, motion, or internal structure. Moreover, the instruments we rely on, no matter how advanced, have their own constraints. Hubble's WFC3 was a marvel, but its GRISM spectroscopy was low resolution, limiting the detail we could extract from GN-z11's light. JWST offers a vast improvement, but even it cannot perfectly resolve faint spectra from galaxies near the observational edge. Detector noise, calibration errors, and instrumental biases all introduce uncertainty. And at the redshift frontier, even small uncertainties can lead to major debates over a galaxy's true age, structure, or distance. Add to this the challenge of contamination. In the search for high redshift galaxies, false positives are a constant threat. Nearby objects, such as dusty galaxies or cool stars, can mimic the infrared signatures of distant galaxies. Light from multiple sources can blend together in crowded fields. Gravitational lensing can distort or magnify signals in ways that mislead redshift estimates. The further we push the boundary, the more careful we must be. Every detection must be checked, cross-validated, and challenged. One misidentified galaxy could upend models, affect timelines, or skew our understanding of the early universe's behavior. And the difficulty doesn't end with detection. There's the issue of exposure time. Deep field observations, like those that uncovered GN-z11, require telescopes to stare at one patch of sky for dozens or even hundreds of hours. This time is precious and limited, fought over by scientists around the world. Observing just one early galaxy can consume more than an entire night's worth of telescope time. Multiply that by thousands of candidate galaxies, and the bottleneck becomes clear. Then there's the cosmic irony. The earliest light is the most transient. Over time, the light from the earliest galaxies becomes more redshifted, more diluted, and harder to detect. The window for observing them is slowly closing. And with each passing billion years, their photons become harder to distinguish from the background noise of the universe. The farther back we look, the thinner the signal becomes. Eventually, we will reach a point, the so-called Dark Ages, where no galaxies had yet formed, and the universe was truly opaque. Beyond that lies the Big Bang itself, hidden behind a veil of plasma and radiation. GN-z11 represents one of the last beacons before that veil. A fragile beacon, yes, but an enormously valuable one. Its detection wasn't just a scientific achievement, it was a testament to how close we are to the edge of what's physically possible. Every observation of a galaxy like GN-z11 is a reminder that our grasp on the early universe is tenuous, delicate, and defined as much by what we cannot see as by what we can. And yet, despite the fragility of the evidence, astronomers continue. They build better detectors, launch bigger telescopes, and write more sophisticated algorithms. They take those rare photons, scattered across space and time, and reconstruct a picture of a universe in its infancy. It is not easy. It is not perfect. But it is astonishing. GN-z11, in this sense, is both a triumph and a challenge. A whisper from a time before structure, before stability, before complexity. Its light is the oldest truth we have ever received, and yet it arrives as the faintest murmur, trembling on the edge of silence. To hear that murmur is a feat of human ingenuity, cooperation, and persistence. To understand it is an act of imagination and science combined. And so we cherish it. We study it. We share it. Because that light is more than photons. It is a message from a time when the universe had barely begun to speak, and we are among the first creatures to listen. When we look at GN-z11, we are not simply observing an ancient galaxy, we are confronting something much deeper. Its light, which began its journey just 400 million years after the Big Bang, has crossed more than 13.4 billion light-years to reach us. It has passed through the early fog of the universe, around clusters of galaxies not yet formed, dodged cosmic dust, and endured the slow stretching of time itself. And after all that, it landed delicately on a detector built by a civilization that only recently learned to gaze up with purpose. That moment, when ancient light meets modern eyes, is more than a scientific milestone. It is a reminder, a profound, humbling, awe-inspiring reminder, of where we are, who we are, and how vast the story truly is. For millennia, humans have looked at the night sky and seen constellations. We built our earliest calendars from the stars. We navigated oceans using them. We measured seasons, foretold destinies, and built civilizations under their steady light. But until just recently in our species' journey, we had no idea how truly far and old that light could be. The stars seemed eternal, like beacons placed for our benefit. GN-z11 reminds us that the sky is not a dome, and its lights are not fixed. They are ancient, dynamic, ever-changing windows into the past. And what a past it is! GN-z11 formed at a time when there were no solar systems like ours. No Earth. No Moon. No Sunday. The very elements that make up your body, carbon, oxygen, nitrogen, iron, did not yet exist in any meaningful quantity. The universe was still in its chemical infancy, composed almost entirely of hydrogen and helium. The heavy elements would come later, forged in the hearts of stars and spread across space by supernovae. GN-z11, forming its first stars, may have been among the first sources of that cosmic alchemy, the beginning of the chain of events that would eventually lead to planets, biology, and awareness. So when you gaze at the image of GN-z11, you're not just seeing something far away. You're seeing the raw beginnings of possibility. The raw beginnings of everything. It puts our modern world into sharp perspective. In an era defined by noise, a distant galaxy, silent and small, cuts through it all. It doesn't speak. It doesn't move. But it means something. Its message embedded in every photon says, "I was here when the universe was young. I shone before stars like your sun existed. I lit the dark when your atoms were still drifting in primordial gas clouds." That is humbling. It also stirs a sense of unity. The fact that we can detect GN-z11, study it, and understand it, means that the laws of physics have remained unchanged for billions of years. The same quantum mechanics that govern particles in your smartphone operated in the furnaces of GN-z11's first stars. The same light that allowed our ancestors to see by firelight is the same light now stretched across eternity, and caught by a telescope orbiting Earth. There is a beautiful consistency to it all, a cosmic harmony that suggests we are not separate from the universe, we are woven into it. This is perhaps the greatest philosophical revelation of GN-z11's light. That it connects us to a time so remote it strains comprehension, and yet we understand it. We decoded its message. We translated infrared signals from an invisible patch of sky and turned them into knowledge, maps, and meaning. In doing so, we proved something extraordinary, that consciousness, which emerged from atoms forged in stars like those in GN-z11, has now turned around and studied its own origins. That realization, that the universe gave rise to something that could observe and contemplate the universe, may be the most awe-inspiring idea we possess. It means that GN-z11 is not merely a galaxy. It is a mirror. It reflects not our image, but our trajectory. From hydrogen to complexity. From stars to sentience. From randomness to reason. And what of the sheer improbability of it? The odds that we would even exist, let alone build tools to detect ancient light, seem astronomically small. Yet here we are. A species that evolved on a rock orbiting an average star in a relatively quiet galaxy, looking back to the edge of time. That is both absurd and magnificent. It tells us that we are rare, but not because we are central. We are rare because the path from GN-z11 to Earth is so long, so fragile, And so unlikely, yet somehow, it happened. We are the result of those first stars forming, of supernovae spreading elements across space, of gravity assembling solar systems, of water forming on cooling planets, of chemistry giving rise to biology, and of biology evolving the capacity to ask, where did we come from? GN-z11 didn't know it was being watched. It simply lived, burned, and glowed. But billions of years later, something emerged from its ashes with the power to see it and wonder. This connection is more than scientific. It is a deeply existential one. GN-z11's light is a message across the greatest divide imaginable. A message that took the age of the Earth itself to deliver. And when it arrived, we were here. We had become ready to receive it. That coincidence, that convergence of time, evolution, and discovery, is not to be taken lightly. It invites reverence and humility. Because GN-z11 also reminds us of scale. It reminds us that our worries, our lifespans, our civilizations are blinks in cosmic time. That our tallest buildings are molecules in size compared to the distances between galaxies. That our histories, important as they are to us, are invisible from a galactic perspective. And yet, in that invisibility lies something powerful. It means that even the smallest, most ephemeral things, like human thought, can touch something as vast as the cosmos. That meaning does not require size or permanence. It requires connection. And GN-z11 connects us across all possible scales, temporal, spatial, elemental, and philosophical. In classrooms around the world, students learn about history by reading books. But the universe writes its history in light. And GN-z11 is one of its earliest chapters. One that was unreadable until recently. One that now sits at the edge of human comprehension, beckoning us to keep turning the pages. What does GN-z11 mean for us? It means that science is not just a tool, it's a form of listening. That astronomy is not just measurement, it is participation in a story far older than ourselves. It means that we are small, yes, but not insignificant. That the very act of looking up, of seeking, of wondering, is itself part of the universe waking up. So the next time you look at the night sky, think about this. Somewhere in that blackness, behind stars and dust, beyond the reach of your eyes, a faint glow still flickers from GN-z11. It shines not for us, but we are here to witness it. And in that witnessing, in that fragile moment of awareness, we become a part of its story, just as it became a part of ours. The question of whether we will ever see the first galaxy is one of the most profound and tantalizing mysteries in all of cosmology. It touches on the very boundary between the known and the unknown, between observation and imagination. GN-z11 may be the most ancient, spectroscopically confirmed galaxy we've seen, its light stretching back 13.4 billion years. But even it is not the first. It is a cosmic pioneer, yes, but it arrived on the stage already glowing, already forming stars, already part of a larger story. The true first galaxy, if such a thing can even be cleanly defined, must lie further back still, buried even deeper in the haze of cosmic infancy. To search for it is to chase a ghost. One that may or may not exist in any form we recognize. One whose light has traveled almost the full age of the universe to reach us, if it still can. One that was born in an environment radically different from anything we can see today. And yet we search. Because to find the first galaxy is to answer the question, how did everything begin? To understand how close we are to finding that answer, we must first define what we even mean by the first galaxy. This isn't as straightforward as it sounds. Galaxies, like stars and planets, didn't form instantly after the Big Bang. The universe began in a hot, dense, nearly uniform state, a soup of particles and radiation. For the first 380,000 years, it was opaque, with photons bouncing endlessly off free electrons in a cosmic fog. Then came recombination, when the universe cooled enough for electrons and protons to form neutral hydrogen atoms. Light could finally travel freely. That light, now redshifted into the microwave range, is what we detect as the cosmic microwave background, CMB. But even after the fog cleared, the universe remained dark. There were no stars yet. No galaxies. Just vast clouds of hydrogen and helium, clumping together under the slow pull of gravity. This period is called the Cosmic Dark Ages. It lasted for millions of years, until the first luminous objects, likely massive, hot, short-lived stars, began to form. These stars gathered in small gravitational wells, perhaps in halos of dark matter, forming the first proto-galaxies. So, when we talk about the first galaxy, what are we really asking? Are we seeking the first gravitationally bound structure of stars? The first accumulation of dark matter and gas? The first object to light up the darkness? Each of these criteria offers a slightly different answer, and each pushes the search further into the past. The first stars, known as population 3 stars, are believed to have been huge, maybe hundreds of times more massive than our Sun, and composed almost entirely of hydrogen and helium, since heavier elements hadn't yet formed. These stars would have been short-lived, exploding as supernovae and enriching their surroundings with heavier elements, or metals, in astrophysical terms. The explosion seeded the early universe with the raw material for future star and planet formation. These first stars likely formed in isolation or small groups, not yet large enough to be considered full galaxies. But over time, these groups merged, accumulated more gas, and began forming second-generation stars. Eventually, these mergers and collapses gave rise to systems we would recognize as galaxies, gravitationally bound structures containing gas, stars, and possibly even supermassive black holes at their centers. The first galaxy, then, may have been the first such structure to sustain ongoing star formation, retain some of its material, and shine continuously in a way we can still detect. The problem is, such an object would be extraordinarily faint and distant. Its light would be so stretched, redshifted to such long wavelengths, that only the most sensitive instruments in existence could even attempt to detect it. This is where the James Webb Space Telescope, JWST, comes in. JWST was designed for this very challenge. Its infrared capabilities, large mirror, and deep field imaging allow it to see further than any telescope before it. And indeed, in just its first year, JWST began detecting galaxies at redshifts as high as Z=13, 14, and even 16, corresponding to times only 250 to 300 million years after the Big Bang. These galaxies, like CERS 93316, may not be the first, but they are certainly early. They give us hints. They light the trail. But detecting something even earlier than these will not be easy. The first galaxy, if it formed at a redshift of 20 or beyond, would have its light redshifted well into the mid-infrared range, perhaps even beyond what JWST can observe clearly. Its brightness would be limited. Its features would be blurred. It might not look like a modern galaxy at all, no neat spiral arms or glowing bulge, just a diffuse patch of faint light, composed of perhaps only a few thousand stars. It could be unrecognizable, a galaxy in name only. Even worse, the universe itself becomes less transparent the further back we look. The intergalactic medium, the space between galaxies, was filled with neutral hydrogen in the early universe. This hydrogen absorbs light, especially in the ultraviolet range, which is the very light emitted by young, hot stars. This creates a fog that obscures our view. Only when enough stars and galaxies had formed to reionize the hydrogen did the universe become truly transparent again. This period, called the Epoch of Reionization, was gradual. It started perhaps as early as Z=15 and finished by Z=6. GN-z11 sits near the edge of this transformation, its light punching through the tail end of the fog. But the first galaxy would be deep inside that fog. Its light would be partially or even completely blocked. This sets a hard observational limit. It's not that the galaxy didn't emit light, we're confident it did, it's that the universe wasn't yet transparent enough for that light to reach us without being scattered or absorbed. So, will we ever see it? The honest answer is maybe. We are on the edge. JWST has shown that it's possible to detect galaxies within 300 million years of the Big Bang. A few tens of millions of years earlier might be within reach. But to go further, to detect the first star clusters forming the first galaxy in the first 100 million years of cosmic time, may require next-generation observatories. One such mission is the proposed Origins Space Telescope, which would be even more sensitive in the far infrared than JWST. Another is LUVOIR, Large UV/Optical/IR Surveyor, a massive proposed telescope that could observe in multiple bands simultaneously. And ground-based giants like the 30-meter telescope, TMT, and extremely large telescope, ELT, may also contribute, particularly through spectroscopy and gravitational lensing. Gravitational lensing, in fact, may be our best ally in the hunt. If we can find massive galaxy clusters positioned just right, their gravity can magnify the light of background galaxies, allowing us to see fainter and more distant objects than our telescopes could otherwise detect. This is how many early galaxies have been discovered already, and it may be the key to catching a glimpse of the true first. But perhaps even more exciting is the possibility that we won't see the first galaxy in the traditional sense, but instead detect its influence. For instance, the 21 cm hydrogen line, a specific radio signal emitted by neutral hydrogen, could reveal the moment when the first stars and galaxies began heating and ionizing the cosmic gas. Projects like the Hydrogen Epoch of Reionization Array, HERA, and SKA, Square Kilometer Array, are aiming to detect this signal, mapping the transition from darkness to light. This kind of indirect observation may be our first confirmation that galaxies existed before we could image them. Like listening for distant thunder before you see the storm, it gives us a way to know something was there, even if we can't yet take its picture. In this way, the first galaxy may be less like a photograph. We may know it by how it changed its surroundings, by how it bent light, by how it nudged the evolution of the universe. And maybe, just maybe, someday we'll see it directly. A tiny smudge of light, so faint and redshifted it barely registers, but carrying within it the echo of the very first spark. That spark will not be bright. It will not be grand. But it will be monumental. Because in that moment, the long arc of human curiosity will touch its furthest point. We will have reached as far back as light can go. We will have heard the universe's first song. And then the questions will begin again. What came before the first galaxy? How did it arise from quantum fluctuations in the early universe? Were there multiple firsts, forming independently in different regions? Was the process smooth or chaotic? And could there be galaxies so far away that their light will never reach us, trapped forever beyond our cosmic horizon? So, will we ever see the first galaxy? We don't know. But the search for it is a gift in itself. It drives us to build, to learn, to look deeper. It unites scientists across disciplines and countries. It challenges our theories and expands our vision. Whether or not we find it, the effort ennobles us. Because when we search for the first galaxy, we are really searching for ourselves, not just our origins, but the deepest roots of the story we are part of. GN-z11 has brought us close. The next steps may bring us closer still. And one day, a telescope will point at a dark patch of sky and find, hidden in the silence, the faint light of the first to shine. There is something profoundly poetic about the light of GN-z11. It is not loud. It does not blaze across our sky like a comet or explode into view like a supernova. It arrives quietly, almost imperceptibly, drifting through the fabric of space, stretched by time, softened by distance, yet still whole. Still real. Still shimmering with the memory of the beginning. When you think about it, that light has traveled for 13.4 billion years. Not through empty space, but across a living, changing, evolving universe. It left its source when there were no planets, no galaxies as we know them, not even a Sunday. Just newly formed stars blazing into existence for the very first time. It passed through regions of space that would one day collapse into galaxies, then clusters, then entire superstructures. It passed by quasars, black holes, and stellar nurseries. It passed through voids where nothing stirred for billions of years. And it passed through time itself, surviving the cooling of the universe, the birth of cosmic structure, and the rise of sentient beings capable of building machines to catch it. And then, after all that, it arrived here. On Earth. Caught by a telescope built by human hands. registered by detectors composed of metals forged in ancient stars, processed by algorithms running on circuits designed by minds that themselves are the result of that same cosmic evolution. What GN-z11 teaches us is that the past is never truly lost. It is written in light, and that light never truly dies, it simply waits to be seen. And when we see it, we're not just observing, we're participating. We are reaching backward through time and retrieving a piece of the universe's own memory. GN-z11 reminds us that we live not just in space, but in time. And that time is vast. So vast that it can contain all of human history, all of Earth's geologic past, the rise and fall of stars, and still leave room for epochs we can barely imagine. We are, each of us, born into a moment. A blink. But that blink, when connected to the light of something like GN-z11, becomes part of a much larger story. One that began before us, and will continue long after us. And yet here we are, at the very moment that ancient light arrives. Think of the odds. Think of the exquisite timing. If the light from GN-z11 had arrived 1,000,000 years ago, there would have been no one here to see it. If it arrived 1,000,000 years from now, who knows what eyes, if any, would be left to look? But it didn't. It arrived now. When our species, against every odd, had just learned how to look deep enough. Long enough. Far enough. That is not coincidence. That is cosmic alignment. Not written in fate, but in photons. In dust. In gravity and glass. In curiosity and effort and wonder. It tells us that the universe is not indifferent, not because it cares, but because it allows itself to be known. And in that knowing, in that silent partnership between what is and what can understand, we find meaning. GN-z11 is just one galaxy. Tiny, even by galactic standards. A speck in a sea of specks. But its light is not just about itself. It is about the journey. The endurance. The message carried across eternity. A message that says, there was light. There was structure. There was something instead of nothing. And now, that something includes us. We who look up. Who wonder. Who build mirrors and sensors and rockets, not just for the sake of progress, but for the sake of contact. Contact with the past. With the cosmos. With the very question of existence. In the end, the light from GN-z11 reminds us that we are not separate from the universe. We are not observers standing outside the story. We are in it. We are made of it. And sometimes, if we try hard enough, we can see back to the very beginning, and find, waiting for us there, a single point of light. A light that has traveled not just across 13.4 billion years, but across the infinite improbabilities of existence to reach us, now. A light from the beginning. And a beginning for those who choose to see. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.